Hey everybody, today's March 12th. Welcome to Propeller Live Forum. And today John is going to be sharing some of the inside workings of his Elite Laser Tag gaming accessory. But before we let JonnyMac loose, I'm going to interest you again in coming to the open house and Propeller Developer Day on May 2nd and 3rd. I think that you guys will mostly be interested in the second day. Friday, we have some schools coming through. And then Saturday, we will kind of stop the tours and just talk propeller stuff all day. So I'm going to paste the link to the sign up into the chat. And if you received this morning's spam, you know that I want you to officially sign up if you're coming. There's several of you who have said you'll be there, but you're not actually signed up. So be like Francis and sign up. You can always back out, but this will help us a lot to know who's coming, how many people are coming, what we need for chairs, tables, freebies, all that kind of stuff. So it should be fun, and the weather should be cooperative around that time of year. People have asked for hotel links, and I will get those together at some point soon. In addition to JonnyMac, are there any other topics today, like any support questions or anybody have anything else they want to share or talk about with Chip that's kind of significance time-wise or important to you?
I have some new math stuff to talk about.
All right. So we got Skippy and math. Anything else? I'm sure things will come up. Okay, so John, are you with us? John McPhalen, unmute yourself.
Sorry, I couldn't find my own button.
John, how do you want to handle questions as you go?
Yeah, that would be fine. I'm going to try to keep this reasonably short. My colleague and friend Joshua Wims, he's online too, so I'll ask him to unmute so he can chime in because he's really the heart of our company and understands more how our customers think and operate. Yeah, I'm the tech guy. But yeah, just shout them out and we'll go. You know, I will ask people to let me finish what I'm saying before asking a question. But other than that, I don't mind, you know, in the stream so that it's contextual.
Perfect. Okay. Yeah, and good to have Joshua here too. We've not met, but we've exchanged a lot of emails.
Yeah, we're excited to come to Parallax Days and have a table. And we're excited about this presentation. John and I have been working on it very, very hard, and it's finally coming to fruition. And we already have several pre-orders on the queue.
Super. And when you come to Parallax, are we going to have a laser tag shootout?
We might. I might send some taggers ahead of time so we can play with them.
I'll bring a few too.
All right, whatever you guys want to do. All right, John, live from Hollywood, California, JonnyMac.
Hello. Okay, let me share my screen. Where's share the whole screen?
John McPhalen.
Sure. There we go. Can you see my screen?
Beautifully.
Okay, so again, I went through and organized this morning, and so I can keep it easy. Battle Tower is an accessory that goes along with our laser tag games. It's kind of a multi-game piece. The idea came up a while ago. We have been working on this a long time, and we kind of did a crudish prototype on a P1, but there's just not enough memory in the P1 for even a basic game set. And one of the challenges that Josh and I face is that our boss and one of our sales guys, they play Call of Duty all the time, and they say, hey, we want to have this feature. Hey, we want to have that feature. Them not realizing that Call of Duty is played on these massive servers. So they have infinitely more computing power than we do. But there are things that we can kind of emulate. And that's part of the reason for this product. Let me see if I can just show my whole screen like that. So anyway, like I said, I think most of the people know who I am. John, people call me JonnyMac. Been around the parallax world since 1994, started with a basic stamp 1 and have created products with every parallax processor except the what was that thing that was
Java stamp, maybe.
the Java stamp. That's the only thing I haven't deployed in a product. Every other processor I've actually deployed in a product. At Elite, we deploy a lot of P1s. We've got about 6,000 P1s in the field and taggers and accessories. Once the P2, this is our first product with the P2. We will be transitioning our major product, which is our laser tag weapon, to the P2 after this. So that's part of the reason this has taken longer than I wanted, and certainly the boss wanted. Part of that is that I've used this project to put together all the framework stuff that we will use in a lot of other products. And, everybody that's a developer knows, you have an idea about an application or an object, and then you put it to real use, and then you find corner cases that you need to deal with. And so we're trying to make sure all of that's ironed out so that going forward, it's a little faster in the development cycle. And like I said, I'm joined with my friend and my colleague, Josh Wems. Josh, again, I'm not blowing smoke up anybody's skirts, and I am trying to embarrass him because he's a really nice, decent guy that doesn't like a lot of attention on himself, but he is the heart of our company. That guy gets in his truck and will drive anywhere to help our customers. And so he spends a lot of time going to youth camps. We're very popular with youth camps, and he will get in the truck and go and do training and service and those kind of things. So I think probably the worst 2 days of his life was having me in the cab of his truck when we drove to Florida last fall, because I'm a chatty guy. Joshua is not. But anyway, we had a great trip. We had a great show. And, we made some changes, to finalize what we want to do with Battle Tower. So the picture that Ken sent out, and I have a version of, is a prototype. Josh has since made some modifications. We'll talk about that. But anyway, we'll move on. So this is that picture that Ken showed, and some of the stuff that we do with as far as technology within this device. Laser tag doesn't actually use lasers, it uses infrared. So I often will say to people, a laser tag weapon is like a giant TV remote that can shoot 1,000 feet. And we do that because we pump a lot of current through the IR LED, almost an amp. And since it's modulated, it doesn't burn up the LED. And then we also have on the laser tag weapon, we have lensing, which will collimate the beam a little bit to make it tighter. So on the top, it's a little hard to see, but if you see a little dome thing, that's the sensor that takes the infrared in. For this particular game, it has a capture the flag mode, and the way that works in our older products, we just had a box with a button on it, and the player would go up, press the button, and if it was an opposing team's flag, then an IR message would go to their tagger that says, "Okay, here's the flag." The difficulty with that, though, is that it was a one-way thing where the flag box would spit out flags all day long. So multiple players could have ostensibly the same flag. Though this is a more advanced product, of course, we've got a lot of stuff in it. So in this particular case, you actually have to go up to the tower and shoot at it up close. And I'll show you how Josh made that work. It's a very clever design thing. And then it knows who has the flag. And so the way capture the flag works is that if let's say, so this is a blue tower. So if an alpha teammate, with a team member, which is red, came to this flag tower and shot it and captured this flag, and then made it back to their base where they have a basic flag box there and pressed that button, then they would win. Now, along the way, they could get defeated. They could get, we don't tend to use the word killed, but I think this is an adult group, so I can say that. So if somebody on the Bravo team kills that alpha player with the flag, in our system, you'll notice one of the technologies I have listed there is XP. So we use XP radio so everybody can talk to everybody else, including our scoring system. So in this particular version of Capture the Flag, when the player that has the flag gets killed, he sends a broadcast message that this tower will hear. And if he says, oh, that's the guy who had the flag, then the tower will reactivate and the flag will be available for another player. So that way, each tower can only give up the flag to one player. So there's a lot involved there. It's with infrared in, infrared out, XB, and then along the way, you can see that we call it tower. So there's 45 pixels that are arranged in a three-sided, arrangement. And so we animate them when it has a flag, and in other games it's animated as well. So anyway, as far as technologies, we have infrared in, infrared out. The pixels, we have a next-gen display, which is a serial interface, but as I think I've said in past discussions, I consider using the next-gen like having 9 cogs, because the next-gen is programmable, and so it's a smart device. So you get a lot of stuff there, and I'll talk about that a bit more. We have wave audio out. Now, for the time being, I'm using Ray Allen's port of FSRW to do this, but we're still waiting on chip for our multi-file micro SD, because we want to be able to play multiple files at the same time. There are buttons. The reason it's pointing to the side of the case is, again, this is an early prototype, and the buttons were up on top by the IR sensor. And but we had an accident at this particular show where somebody reached up to touch a button and knocked over the case, and everybody was worried. But Josh did such a nice job on the mechanical design that we had a small bracket break internally, but no other problems, or at least we didn't think we had any other problems. Till a few seconds later, we said, hey, what's that smell? And all of us that have worked in electronics know that smell. And what had happened is that the edge popped out of its socket, and on the original board we had open pin servo headers that had 5 volts on them, and we think one of those shorted out. Luckily, we use an off-board 5-volt power supply, and so it killed that, but it didn't hurt the board, and we replaced the 5-volt power supply, and everything was fine. And now we have a bracket that holds that edge in. But other technologies, like so, we have XB, we have RS-485 that we're going to deploy in the future for DMX. We have I2C available. We don't use it in this particular product, but we have another product that we've done a P1 prototype of that is used more in the airsoft community, and that needs I2C. So we have I2C ports, and we wanted to serialize the board. The edge has a serial number on it, but if you pull off the edge, then it's not mated to the board. So one of the things that we did was, as you'll see, I put a DS18B20 one-wire temperature sensor on the board. So it helps us in 2 ways. It serializes the board since it's soldered to the board, and it gives us the internal temperature. So since these are outdoor devices, and this is a new product, we want to be able to monitor that, and we can. So anyway, I'll say out loud, and I think most of the people in the group know me, I don't do anything terribly complicated. This is just a lot of stuff all packaged together. So these are lots and lots of utilities and objects that I've written over the years and now ported to the P2. And you'll see where, the P2 really helps us out, because if I did things the way I had done them in the P1, we couldn't fit it even in the P2. We'd be using too many cogs, and we'll discuss that in a second. But so here's all the stuff. I think it's really what I was just talking about. It's a P2. It's primarily written in Spin 2, but obviously we have some, or maybe not obviously, but we do have some PASM 2 drivers, like the serial driver and a few other things. And several places where I use inline PASM, and that's a huge help for saving cogs in our case. We have the next gen HMI, IR in and out. There's buttons on there. And one of the small things, with the P2 that is a savings in the P1 with our laser tag, because there's a lot of wiring in the tagger, we feel it's necessary to debounce the button inputs. Well, the P2 has pin filtering built in. So that helps. We don't have to worry about it. We know that when we have a pin, it's a good input. We have 4 channels for pixels and servo outputs. On this particular case, we're only using 1 channel. As I was saying, that other product, which is called Control Point, it has multiple pixel output requirements. That's why there's multiple channels. Wave audio, as I was saying, we're using Ray Allen's FSRW. That actually, to play a wave file takes 3 cogs, because there's one used by the file system, and then there is the player, if you will, which takes the sample and multiplies it by the volume and spits it out a DAC. It's a very small cog, but it has to run in the background, so it can run at any time. And then in order to make sure that long wave files play smoothly, it's a spin cog that is a double buffer. So we have 2 buffers. We fill them both up and then tell the background to start playing. And when the background is finished with 1 buffer, it marks it. And the foreground, which I think the method name is called buffer stuffer, when it sees that a buffer is empty, it'll read more from the SD and put it in there. So it's a simple, very simple little double buffer, and it allows us to play wave files without any hiccups at all. As I mentioned earlier, we use XB for our wireless communications. There in the P1 laser tagger, we monitor the battery using an INA 219 chip. So that's a battery monitoring chip. So that, luckily in the P1, we can just drop that onto the EEPROM lines, and that way we can monitor battery voltage. So we can tell a player, hey, come back in, we need to give you a new gun because your battery's getting low, etc. It worked out very easy in the P1 because we just have a voltage divider, and we take that right into an ADC pin, no problem. So that was, we went from I don't know, it's a $2 or $3 part, the INA, to 30 cents worth of, 2 resistors and a cap for the battery monitor in this. As I was saying, we use the DS120 or DS18B20 one-wire temperature sensor. In the future, we have RS-45 now on the board. In the future, we will deploy that as DMX. And then I mentioned I2C. So those are all the techs. And so I wrote all of the code for this except FSRW2, which I appreciate Ray did that. I had to make a small change to accommodate something, but otherwise it seems to be working fine, and we have all that going. But it's, again, nothing horribly complicated, just a lot of it. This is what the PCB looks like without the edge plugged in. I did that for 2 reasons. First off, then you can see back here because I didn't, I just wanted a static image. And the other thing is dip trace is horrible with, Michael made a nice model of the edge board, but the other day I tried to load it into this model and it took a full hour before it would display. And I thought, okay, I just don't want to mess around with that. But this is the clip that I was talking about. So it's just it's a 3D printed clip with a couple of metal inserts, melted in, and then screwed them in the bottom. And in fact, I think I have, let me go to, here's what that looks like with the edge plugged in. So there's a couple of millimeters up there. It's enough to keep it in, but it gives us a little bit of wiggle room. So that's what that is. This is Josh's model of the tower. As I was telling you, the buttons were up here. They moved down to these sides, and there's one on the back as well for the Charlie team. Our system is set up to accommodate 4 teams, although I think 99% of our users just play Alpha and Bravo, but we accommodated Charlie on this. Our accessory devices, we always stick them onto the Delta team. And one of the things I was telling you about with the infrared, so this is the sensor, this part right here. The reason it's knurled like that is it's actually threaded. So you can spin that out and it comes up and it puts a tube around that sensor. And this is when we're in capture the flag mode, where we don't want somebody to be able to capture the flag from a distance, which wouldn't work anyway, because the sensor, this is a low power sensor. And so what happens is with that, it forces the player to go right up to the box, shoot down into the tube, and then the tube spits out the IR that gives them the flag. So it's a really neat design that Josh did for that. And then I think if I press forward, that'll get, yeah, so speaker is back here, but pretty straightforward. Now, there's quite a lot of stuff in here. There's a really big battery, and then the circuit board is mounted on top of that with a frame. But Josh has put in an enormous amount of time on this design. It's quite nice. The elements inside are actually, we're using PCBs. They're not really structural because we have this tube holding everything up, but we're just using the PCBs with the pixels on them, and they're set up so that we can very easily daisy chain them together. Because again, we have 3 sides of 15, but we treat it in the code as 145 pixel strip, because that lets us animate it any way we want. So we can do twirly things or anything else. Whereas, we had originally considered just having 15, all 3 sides doing the same thing all the time, but that limited what we could do visually. And having a strip of 45 was not problematic at all.
And this was a lesson in iteration. Fail early and fail fast. We originally had it divided into 5 LED pieces, but soldering them and getting them all aligned properly was not easy. So we decided just go with a longer board.
Yeah, we had thought, oh, if we have these 5 segment strips, then we could make these, and then they were thinner too. And what we were able to do with that, but then thought, okay, it's not really worth the headache, is we could solder 7 of them together and arrange them horizontally to create digits. But it just became more work than it was worth. So it's one of those things where we say, hey, let's be super flexible. But the flexibility really became more problematic than it was worth. And we just said, okay, let's just simplify this. And these are very easy to build. They have JST connectors and little jumpers go between them, so it goes together pretty nicely. So that's so going around the board, as I was saying, we use 5 volts external of the board, and part of the reason is that we don't want to run too much current around the board. With our pixels, that's the worst case, and that's about 1.25 amps, so that's easy to run. In the control point project, that has a lot more current requirements, so we use external power supplies, so that just made sense to do it this way. This JST connector here is for the battery. So the battery has just a JST wire that goes directly to the board, and that's just to monitor the battery voltage. Then the battery also connects to the external 5-volt supply, which comes into the board. That the connectors for that are hidden by this bracket. I'll just go around counterclockwise. So this is obviously the SD circuit. This is the audio amplifier. It's a mono audio amplifier for the time being. This is the XB socket. Now, one of the things that we did do for flexibility is we stuck in this little 8-pin socket. This is the same socket as on the P2 accessory boards, except it's only 4 pins wide. And the idea behind this, and we've done a little bit of experimenting, we haven't finalized it yet, but we know this connection works, is to be able to replace the XB with an ESP01 if we wanted to put this on a Wi-Fi network. So that's the idea behind that. This is our RS-45. Now, even though our intentions, at least for Battle Tower, we will ultimately release it. We will have a variant that has DMX output. It is a full RS-45 circuit. So again, when we deploy this to other products, we could do half duplex to it instead of, DMX is just a one-way output. But the circuitry is capable of doing half duplex RS-45. This is the next gen connector, which is easy because it only needs a connector. Everything else is the same. These are our pixel outputs. We have them kind of in two forms, depending on what we're using. These chips are my favorite little accessory. I put them in things all the time. It's a TC4427. It's a MOSFET driver. So you get 3 volts in on one side, 5 volts out with really stiff current out of the other. Again, they're MOSFET gate drivers, their intention. This was a chip Phil Pilgrim told me about a long time ago. I've deployed it many, many times as an actual MOSFET driver, but I use it a lot for driving pixels and servos, especially over long distances. These connectors are our sensor connectors. Our standard sensor has 7 connections, so it has power, those ground 5 volts. This is infrared in, infrared out. And then the current gun sensor has a common anode RGB LED on it. So these little NFETs here will switch the LEDs. In the future, we will probably have pixels on those sensors. So I went ahead and accommodated that. So instead of having 3 pins for color LEDs, there's just 1 here, and that's going through this. This is I think a TC4426 or 28. It has 1 active high output and 1 active low output. So the active low output we use for driving the IR out, and then the active high goes to the pixel. These are our button inputs, easy peasy. This TO92 is the temperature sensor and serial number. And then finally, we have 2 I2C ports. This JST is 5 volts. So there's 5 volt, there's a 5 volt level shifter circuit there. And then this is the quick connector, which is very popular. We put them on everything now because they've become such a standard. So that's 3.3 volts. But again, there's nothing terribly complicated about this. It's just a lot of stuff, and organized together. Okay, well. So one of the things that that happens, so there's lots of objects and several thousand lines of code. But one of the things that what I do in my code is I mark cog usage. So easy, the main application requires a spin cog, and then I will mark here. And as I was saying earlier, the wave player requires 3 cogs. Next gen uses serial output. XB uses serial output, and the IR input. Since IR is an asynchronous event, we have to use a background cog. We never know when it's coming. I may not have said it before. I made the quip about the TV remote. Our IR protocol is based on a thing called miles tag, which is a protocol used forever by everybody, essentially. We use a slight variant of it, but it's based on the Sony infrared protocol. So it uses Sony bit timing. And so it's very easy to deal with. But one of the things, in the P1 tagger, we have 3 cogs for audio. The difference there is we use an external DAC because we don't have DACs on the P1. And so we use a SPI DAC in there to get us down to 3 cogs. And there is infrared in, infrared out. There is a PWM cog to run the LEDs, and then the XB cog which is serial. So we use all 8 cogs in the tagger, and we're doing a lot more here, but this is where my favorite feature of the P2, aside from, you know, the really nice assembly, is inline assembly. So if you ever see one of my objects and you see this underscore NC at the end, that means no cog. Normally in the past, like if you look at any of anybody's WS2812 code that runs on the P1, it requires a cog because of the very strict timing requirements of the WS2812. Well, in the P2, we can do inline. And so where from a decision standpoint, we'll look in our particular case, we're only the only time in this product where we are using infrared out is in the flag, and so that's an aperiodic and a very short thing, doesn't interfere with anything else. So that was an easy decision, and so that was on the IR here. So there's our IR output. Same thing with the WS2812. We only have to update 45 LEDs, and at 800 kilohertz, you can do that really quickly. And I have the timing here. Same thing with the temperature sensor, which is 1 wire. Now, the reason I don't have underscore NC on the end of this is because the only 1 wire object I ever did for the P2 uses inline assembly. So I've not written a version that requires a cog, because, you know, most 1 wire stuff is aperiodic, and it doesn't, there's no need to consume a cog for it. But all of these with boxes around them are things that in the P1 require a cog that don't here. And then the same thing with the DMX. DMX, for those anybody unfamiliar with it, it's a very simple serial protocol and I'll show you what it looks like. I have a capture, but it's serial. Now in DMX, what DMX calls a universe is technically 513 bytes. There's a start byte that is always 0, and then there's 512 slots or channels. That's why you'll hear it called DMX 512. And now ahead of the start byte, there is a 92 microsecond break pulse followed by a 12 microsecond mark after break, they call it. And those numbers are in the spec from the transmitter side. What the receiver looks for is 88 and 8. But from the transmitter, you're supposed to send 92 and 12. But you know, when we decided to do this, then I got a little nervous because I was thinking, oh shoot, now I need a DMX transmitter cog, which is not hard to do, but then I would be at 8 cogs, and I really don't like doing that with a brand new product. As I said earlier, I started with the P1, so I'm very stingy with resources. Sorry, not the P1, the basic stamp one. The basic stamp one had 12 bytes of memory or something, you know, very small like that. And so I just became very stingy with resources. And at any rate, then I started thinking about it. And this is where what also helps us in this particular case, to a degree, are smart pins, because DMX is just serial. Now, there is the break pulse that you have to do, but it's very simple to turn a smart pin off and back on. And that's what I do. And I'll show you that, actually. But, you know, again, all fairly standardized stuff. I will say it over and over. I don't do anything complicated. I just do a lot of simple stuff and try to build products that make our customers happy. Here's the way I saved cogs using inline PASM. So as I said, with the WS2812, there's 45 pixels, and at 1.125 microsecond per bit, 24 bits per pixel. That's just over a millisecond to transmit. Not a lot of time in the scheme of things. Our IR out, that can be a little variable, but that's so aperiodic. You know, the pixels have to be updated depending on the mode the game is running in somewhat frequently. So that's why I cared about that. Again, in the future, we're going to do DMX, but one of the things I found, you know, working in air quotes Hollywood and doing, I've been doing DMX stuff since the days of the SX. The first DMX code I ever wrote was for Disneyland using the SX28. And you know, so the thing is, when you're transmitting DMX, you don't have to transmit a full universe, since the receiver uses the break signal to synchronize on everything. So in our particular case, Josh and I, we have a product now, a P1 product that does simple DMX out. And the fixtures that we've used, and we know we're only ever going to have one connected to an accessory, generally use somewhere between 3 and 7 or 8 or 9 slots. You know, so for example, the simplest fixture, although I've never seen one recently, would have a red channel, a green channel, and a blue channel. I have a couple of lights that I just got from Amazon that their simplest mode requires 4 channels, because it's got a master level and then red, green, and blue levels. And so that's 4 channels. And then, you know, we have some other fixtures that have other modes, so they take more. But so I just settled on 10 channels. Well, if you do the math, again, with, you know, the 92 microsecond break, the 12 microsecond mark after break. Oh, that's not supposed to say I. That's supposed to be microseconds. 44 microseconds times 10 slots, you know, it's half a millisecond. And so that's not a problem. So that saved, you know, instead of having a cog that's spitting out a full universe. A full universe takes about 23.5 milliseconds. That is too much time. And I don't need it. So we're doing a modified DMX. As I was saying earlier, the one wire, the only driver I've ever written for the P2 uses inline, so that doesn't take a cog. And then I2C, which in the P1, the I2C, my simple I2C stuff just runs in spin, because since I2C has its own clock signal, it can run really at any speed if it's slow. On the other side of that, though, the P2, even, you know, I kind of go middle of the ground. I run my projects at 200 megahertz. You know, if you do I2C in spin, it runs greater than, unless you insert delays in there, it will run greater than 400 kilohertz, which is kind of considered normal fast mode. And there are a couple of parts we have that want to run 100 kilohertz. So by using inline assembly for I2C, the timing stuff is sorted out and it runs exactly what we tell it. So again, my favorite feature, I remember Chip talking about it in a meeting, saying we were going to have the ability to just stick assembly into spin code. And I got very excited about that. And I will say, Chip will tell you, and he'll smile right now, because when he and I talk privately, I give him a lot of beef. And, you know, he's my friend and he takes it. He understands, because I'm a developer and, you know, he wants the best for me. But I'm so happy to have the ability to not only to have a nice assembly language. I was telling somebody the other day, maybe it was Ken, I bought the assembly language book for the RISC-V, and it's a nightmare. Going through that assembly is just horrific. And, you know, because I'm not like the, you know, the gurus like Chip or Ada. They're really super, you know, brainiac assembly programmers. I'm not one. So I like that P2 assembly is so nice and clean, and even I can understand it and make use of it. Oh, is that the last of my slides? I guess it is. So the I think I mentioned, you know, this is a capture to show DMX, and so, you know, it starts with a break. There is this mark after break, and then everything else is just a byte. And so it's really easy. And in this now, you know, it says 588 microseconds. So again, less than a millisecond to transmit that whole thing. And in code, the assembly code to do all that is just this. It's really simple. Now, in this particular object, I start the transmit pin, you know, in spin, and to set it up that way. And then when we're going, because it'll leave the line at the idle state, And then when we have to when we call this show method, which means, okay, take whatever's in the DMX buffer and pump it out, then it will clear the smart pin mode. Now, thankfully, the way smart pins work is you can clear the mode without clearing the smart pin parameters, the X and Y stuff, X in particular. And so this disables the smart pin. This will drive it low. In this particular case, what I found, it's since the cog has these PR0 through PR7 user registers, this will copy my my global values that are the configuration for the driver to the cog registers, and then everything is in the cog. I found that's a little faster than having local variables here. But there it is. It's stupidly simple. Because once we've done there's the break. We take the line high and wait. There's the mark after break. We set the pin back to being a transmitter, the asynchronous serial transmitter. Again, the baud stuff in the X register didn't get obliterated, thank God. And so it keeps that. And we pass. One of the parameters is the address of the user thing, and it just goes through and sends them all out. Stupidly easy and works really nice and cleanly. And technically, this can be used for any site. If somebody wanted to, do a show control and use this with a full DMX universe, you could. It's just that this method blocks during the transmission. In my case, it's 0.5 millisecond. If you're going to do a full DMX universe, it would be about 23 milliseconds, but that might not be a problem for some people. So again, thank you, Chip, for inline assembly. That I like it a lot, and I couldn't have done this project the way I'm doing it, without using a compiled language. I love spin, and this allows me to have the best of both worlds. But at any rate,
we added org H now, so if you want hub code, you can just put org H.
I tried that, and it runs slower, so I took it.
Yeah, it does, because looping it starts faster, but looping is going to take longer because of the hub memory issue.
No, I'll show you one of the things. Another thing that when I'm talking to non-propeller people about the benefits of the propeller, I talk about stuff like this. So you can see here, I'm doing a timing test. So this shows that my code to do start plus is actually 548 microseconds.
So that's neat. So that DMX show that outputs the whole schema.
Yeah, but I remember I'm only doing 10 channels. So I'm outputting the break, which is 92 microseconds, the mark after break, which is 12, and then technically 11 bytes at 44 microseconds each. And this I should probably add 8 here, because because I know that I'm not going to be coming back. You'll see that once I've written to the pin, the last one, I'm out of there. So technically I'm exiting back while the last byte is transmitting, but I don't think that's a problem. Because I'm not going to be updating this very often. One of the things I found is that, so I was doing a test with my timer, some fixtures, in fact, when I was doing work with Disneyland, they said, hey, and this was on an original P1 board. We had a 2-lead red-green LED, so it could be red in one direction, green in the other. And then we had some background code that would swap it, so we could create yellow and flash and all kinds of things. But they wanted to have they used that a lot. Since it had the RS-45 circuitry built onto that board, they used it a lot for DMX projects, and they asked me to add to the driver the ability for them to see if the DMX signal was gone. And so, it was easy. I just had a timer running in the background. That's where one of the things I do miss about the P1 relative to the P2 is just the free running timers in the cogs, because in my DMX code in the P1, I just use one of the free running timers. Every time I get, there's a signal change, I just reset it to 0. And then in between things, I look, and if it gets up to 1 second and ticks, and I say, okay, we lost our signal. So it's a little bit different, but the, yeah, I lost track of where I was going, but at any rate, still with the P2, super clean and super easy. And again, in my case, and this is just my style, I don't want to send out V1 of a product with all 8 cogs in use, because that feels like, we know that, people had a really good reaction to our early, show we showed a few months ago. And, we made some improvements in, so we know once it starts deploying in the field, we think we're going to get some buzz. And then Josh and we're not dreading it, but we know it's coming. Is the boss going to say, okay, good job, now I want this. And I just want to leave myself resources for this. And I think I have. So at any rate, yeah, I think I showed everything that I was going to show, unless anybody else has questions. Again, a lot. It's all easy stuff. It's just a lot of it. And like I said, right now it's about 4,000 lines of code, and I have some more work to do. And that's the main that's not all the libraries. Lots of libraries.
Show the guns.
Pardon?
Yeah, I'm curious to see the guns.
I don't have a picture handy. If you go to, what is our website, Josh?
elasertag.com.
Yeah, elasertag.com. Oh, here, since everybody can see my screen, I guess I could do that. I can't get to I'm trying to move there we go. I'm trying to move the meeting stuff out of the way so I can get to the search bar on my browser.
They look kind of like ping pong ball guns or something.
Yeah, so because we do so much work with children, we do have them in black, so they look a lot like weapons. I have black ones that I had to paint orange because I was taking them out to the park to do some range testing, and I thought, oh, this is Los Angeles. I could be shot by cops with this thing.
Yeah.
Because you'll see, like, here's an alpha tagger, what would probably be an alpha tagger since it's red, but this is a standard scope that you can get from any gun store. This is a standard stock that you can get from a gun store. So we have, they're molded in. We have Picatinny rails that will hold normal accessories. Now, most often people get them like this. So they even though they're biggish, and people treat them like pistols. You put a stock on them and they become a rifle, and you put a red dot scope, and that way, especially the people who are doing outdoor. Like I said, we worked, now the original circuit design that I modified. So the original product that was with the company when I met the original owner of the company was based on a PIC. And they had a clever design for doing the infrared out. And so I borrowed that, and I think I improved it a little bit. And so now the best case test that we've ever done was on a moonless night in the desert on a road, and it was like 1,600 feet.
Wow.
And so, that's not normal playing conditions, but routinely outdoors a couple 100 feet, it's not a problem.
How many radians is your spread? Like, how fast is it?
It goes, well, Josh and I just did a test last year on that. Josh got a basketball court that we were able to shoot off all the lights, and we made some sensors. And I think was it 11? So the beam was 11 feet wide at 100 feet. So there is a little bit of spread still.
Yeah.
but that makes it, I mean, if it was laser-like, kids would, again, we
They
cater so
wouldn't,
much to
they wouldn't hit
children,
people very
you would
often.
never hit anybody, and
Yeah.
that would defeat the purpose of it. So one of the things Josh and I have talked about in the next generation is making that a little more tunable so that you can narrow it down. So we'll see. Now, interestingly, so these are all plastic, but when I first started with the original incarnation of the company, I was in the office in Dallas, and a call came in, and it was really kind of mysterious. And the owner was talking to this guy, and he said, "Wow, that was really weird. Somebody's saying they represent a celebrity and they want to know a bunch of it." Anyway, to shorten up this story, they went round and round and round, and then he said, "Okay, come help me." And we used to have metal taggers. They're very heavy, very anyway. The next day he flew out. When I flew home to California, he flew here too, because he took all those taggers to Elon Musk's house for a party for his son, and then to show his security people, because they wanted to be able to use this for not to actually protect anything, but to do training around their facilities with our military style guns. So now, most of them are, again, we're very entertainment oriented. We don't have those tactical ones. As you can imagine, they were very expensive to produce because they're made out of machined metal.
Yeah.
And then too, the other thing too is then you had to use XPs with external antennas, and so they're nice. I really like them. I have one, but they're very expensive.
And there's operators that will never move away from them, and therefore they are staying on the legacy system.
Yeah. They won't upgrade to the new boards because they like that old one.
Well, you guys could make this. You could make a version that was machined it's functionally similar, right?
We could. It was just, probably wouldn't get very many sales because it would be expensive.
But maybe those guys would upgrade that way.
Yeah. No. So then the next step, of course, like I said, is the P2. In this tagger, right in this section here, there's the P1 board. And this is where, I think Ray Allen, I mentioned earlier, he's building those P2s that fit into a socket. I would really like that for our tagger parallax friends. Build it and we'll buy it. I don't need the memory though. Everybody, I'm not a gamer. I'm never going to build video games out of microcontrollers. I just want I would love to have the edge circuit with a real-time clock in that castellated edge version that I could put into a socket on the board. That would be fantastic. Because I don't think I can fit an edge in here. Now, we're going to make a new body for the next generation, but the boss has asked Josh and me to work as hard as we have to try and fit a P2 into this tagger. So on the board, you can see that little module there is the sensor. Our things, we do have external sensors that go around the person's head. They plug in there. Another reason for that ESP01 socket is to give us another platform to experiment with. We're looking at using in the next generation tagger. Of course, its main processor will be the P2. But we may end up using the ESP01 as a link to a wireless headset. That's something we've been experimenting with because we plug in wires now, and most vendors do, but no customer is happy with that because kids get rambunctious and they break wires and it's a pain in the neck. But nobody has been successful, really, correct me if I'm wrong, Josh, at a really good, really reliable wireless headset.
Not that I know of.
So we're hoping to solve that. We're looking at ESP01 because they have an internal protocol called ESP Now that once you've connected MAC addresses between two devices, they'll stay connected. And Josh and I worked out, we've got it all on paper. It's just that, we can only do one serious project at a time. So once we finish Tower, then, you know, we've got a couple of small projects, but once we get into the Tagger 3, we call this Tagger 2. We call the legacy product Tagger 1. The Tagger 3 has to have wireless headset, so there will be more work there. Hopefully, you know, that's not a huge effort, you know, where you're just using ESP01 as a serial bridge to the ESP Now protocol.
John, I have a question for you.
Yes, sir.
Is there anything that you're thinking about incorporating something on your main unit? Who has the flag?
When you say main unit, what are you talking about? What you were talking about, the tower?
Yes.
Yeah, the tower knows, because to get the flag, you have to shoot the tower. Oh, and so I guess I should have explained that. Whenever in our IR shot, it's 15 bits. 7 of those bits are your player ID, and 2 of those bits are your team ID. So when you shoot the tower knows who has the flag. That's why when a kill message comes across the network, if the defeated player in the kill message matches who had the flag tower will come back to life. So, you know, the flag has the flag, when it's in flag mode, it has an animation running on the LED, so a player can go over there and shoot it. When that happens, the animation goes out because the flag is now with the player. But if the player gets killed along the way, our kill messages are broadcast, so everybody on the field, taggers and every accessory, hears that message, that works to our benefit here. We did that originally so that the taggers could keep score, and you didn't have to have a computer system to score the game. You could just look on your own tagger. So we use that, you know, fortuitous, you know, feature, so that in capture the flag mode, if the person who has the flag gets killed, the tower says, okay, you're down, and it turns itself back on so another player can pick up a flag.
Okay, I was just wondering if there's some sort of a numeric display or alphanumeric display that would indicate a number or identifier of the person who has it.
Well, the only person near the flag, the tower, is going to be who's getting it, and there's an audio output. Remember, so we have audio, and there's also audio on the taggers too. So when they pick up the flag signal, they'll get an audio indication that they actually have the flag, and then they can head back to their own base.
Okay.
So there's audio feedback there.
It wouldn't be good to like cause the guy carrying the flag to have like a bright blue flashing LED.
Oh no, yeah, no, that's how you know somebody has a flag. This sensor here has LEDs in it, and it will be flashing. So if somebody's running across the field with a flashing sensor, you know they have. Yeah, so yeah, you have to be able to identify who has,
right.
You know, so yes, no, that's always been part of the game, is whomever has a flag is identifiable on the field through LEDs.
Okay.
Yeah, I got it. Makes sense.
Now, longer term, because we do have a computer system, you know, involved in all of this. Longer term, probably what will happen is that there will be a special message that the tower would broadcast. It would only go back to the computer system that says, hey, this player has the flag, so we can put it on a scoring screen. But again, we're kind of doing things iteratively in this mode, because right now our flag boxes are dumb. You know, nobody has like I said, in our the problem that we have is that the flag boxes right now is just a button, so it'll just spit out flags to anybody. And so, you know, this case, you know, since we're using the shot to do that, we can identify who has the flag.
Do you use that, or are you going to use that to keep a running score for each team?
Yeah, we do that now. We have, that's what I was saying. So there is a kill message that goes out. So whenever, let's say you're on Alpha team and I'm on Bravo team, Grover, If you shoot me and I run out of points, I'm defeated. My tagger will broadcast a global message that says Grover killed me. And so everybody knows that, and it will do it. But let's say you're Alpha 1 and I'm Bravo 7. And so, you know, the message goes out. It has a header on it that says this is a kill report and Alpha 1 killed Bravo 7. So that way every tagger and the computer scoring system can keep track of that. So we do that now.
But my question was related to keeping score and having to be updated for each team as the flag moves.
Well, the flag is not a scoring event. It is a game. So what happens? Let's say you get you grab a flag and you make it back to your base and you press the button on your simple flag box. The way the tagger works is if you press your own flag box and you have an opposing team flag, you won the game, and your tagger will do a broadcast message that the game is over. So there's no score involved. It's just you can outright win if you do that. So again, this is why where we use XP, and we do send a lot of broadcast messages in the system so that everybody can keep track. So again, if you defeat somebody, that message will go out from the defeated tagger. And so the scoring system at the computer plus every tagger, again, we have a lot of family operated businesses that operate out of a trailer, and they'll go to a city park and set up games with kids. And you know, at the end of the game, you say, okay, who won? Well, you'll see here on the tagger, there's an LCD and we have some buttons. So you can go through there and you can see every team's score, and it'll tell you who won. It will also give you reports. Like we have this thing, it comes from I think it comes from the big military games called kill death ratio. So you know if you were effective or not. If you have a high kill death ratio, it means you killed more times than you were killed. So there's those kind of things.
I didn't know if you kept a running score that is incremented as you go through the game.
Yes. Because
every time somebody captures a flag.
Well, again, the flag is not a scoring element unless you make it back to your base. Okay. So you don't know who has the flag except by the indication of a flashing LED here. Right. That's not, at least right now, that's not reported. Because as I said, our current flag boxes are just little tiny microcontrollers that all they do is spit out IR signals. And then we count on the tagger. You know, again, the rules are if you have the opposing team's flag and you press your own flag box, you win. And so and then your tagger, since it has the ability to communicate to the entire system, will send a, you know, it plays an air raid siren kind of sound as an indicator that you won, and it sends a broadcast game over message so the game will shut down. Now, again, Josh and I are working with a lot of legacy code. Now, I ported the code to the P1, but you know, every time we talk, we're looking forward to a day when we're not kind of handcuffed. But we have a lot of customers that like the code base as it is, even if it's not as flexible or as nice in some areas as we'd like. But we'll ultimately get there. What Josh and I are both trying to do is just create the flexibility that we need to handle what people are doing now and give them what they ultimately ask for in the future. Sometimes you have to show customers. You know, I've been doing product development for a long time, and sometimes, you know, people are born in Missouri, and you got to do the show me thing. And so, you know, and we will, and we're happy to do that. Again, this is where Josh is a master. He goes out and, you know, gets people trained, and he understands the context of, you know, all of the features, and is able to get people up and running really quickly again. And because we're cost effective, our product is very reliable and works well. You know, it's very, very popular. And so we don't want to, again, you know, because every time I have a conversation with the owner, I'm saying, you know, I wish we could do X, Y, and Z. He said, nope, you can't right now because we have to be able to port back. In fact, when we do the P2 version of the tagger, it's going to operate just like the P1 version initially, so that we can get everybody over to the, when they have P2 taggers, then we can unleash a lot of other features that, you know, we're not able to accommodate in the P1.
Hey,
Well, that's all the questions I had.
Sorry?
That's all the questions I had. Looks
Oh,
great.
okay. Yeah, thanks.
Hey, John, can you talk about the temperature sensor serial number without giving away the store?
Oh yeah, well, no, that's not a problem at all. In fact, I think in the forums I posted some of that code. So it's a DS18B20. You know, it's a very simple, you know, one wire C. All one wire devices have a unique 16-bit serial number. Hang on one second. Let me grab a P1 off my shelf. I have a P1 board with a let me go to I don't know. Sorry, the reason is, yeah, I'm trying to move around the boxes for the thing. Let me go to file, open from P1. This is my, yeah. Let me do this. JMPS 1820B demo. Okay, so this is on a P1, so it requires a cog. But if I run this now, oops. Hang on, this is an old, that's an old version of that program. Let me do this, open from, I think I had one. I accidentally stuck it in here. There it is. All right, so this should be, I need that to be 0. And am I doing, okay, so I can run this and open up that. So this is, oh, this is not at the right baud rate. Sorry, I'm not, I'm more used to running PST. Let's do this again. Oh, come on. Well, I'm gonna ask you to trust me because here, Walter, one more try. I'll go to.
We know how this goes. Don't worry about it.
I will go over to Propeller tool because I just put this up into the forums the other day for somebody else. So anyway, what I was starting to say is that every one wire device has a unique serial number in it. And so one of the lower cost one wire devices is this DS1820. And so we get a serial number out of it, you know, that since it's soldered into the board, it's there. And let me see if this will work now. F10, F12. I think that was 35. Oh, you. So in the one wire, I'll explain what's happening. I don't know why, because the circuit is the same as I've been using. I'm just going to try a different pin. In one wire, it's an open drain kind of circuit. It's a half duplex. And So what happens is the master side pulls the, okay, I don't know what's going on with my circuit. I guess here, I'll get one more try. I have another sensor here since I bought a bunch of them. The mother, the when you are first talking to a one-wire device, there's kind of a reset pulse to it, and then you check for what's called a presence pulse, where the one-wire device will pull the, I am in pin 1. Oh no, shoot. Sorry, my bad. I have it in my, I have a breadboard attached to my P1 eval, and I had the pin numbers wrong. That's why it was all. So in when it says bus short, it looks like the presence pulse is low, and then it's low after that. So it was just because I had it on the wrong pin. It was supposed to be pin 16 before. Now it'll run. I moved the wire. There we go. So here's the output from that. So this is the unique serial number from the DS18B20, and then there's the temperature. So this is unique to every one-wire device. And so again, it was, and there's a whole bunch of them, but you know, I thought, well, for our use, since this is an outdoor product, it might be useful to know what the internal temperature of the box is, since we do have a battery in there and it's sitting out in the sun. You know, again, with the P2, now I'm doing it with the P1 here, but with the P2, this doesn't require a cog rather. You can do this in line. But
So that
I grabbed the
serial number is unique to each
to every single
sensor?
one-wire device. Yes.
So each one has a different serial number.
Yes.
Okay.
Even it's the same. So for example, in this, the 28 right here, that indicates that it's a DS1820 device, a temperature sensor. And then this is the CRC of the rest of it. So that should be unique, but technically this is all the serial number stuff. And here, watch for just a second. I don't know if this is going to scream. I'm going to swap out another sensor and rerun it. So remember those numbers, John.
Okay.
And I'll swap in another sensor and rerun the program. F10, F12.
Okay, Hoffman, what were they?
Yeah.
But you can definitely tell they're different because there wasn't 3 zeros in the last one.
No, there was 66.
And it was 66 at the end. But you notice that 28 is the same because in the one-wire serial number, that's the device type. But
cool.
So again, this gave us a way to serialize our circuit boards and gave us something useful to, you know, to understand. So, oh, the one thing I didn't show, because the next gen, again, is one of my favorite accessories, as John Huffman well knows. I started experimenting with the next gen just on my own because I'd seen it on YouTube and I was tired of all the schmarshmino demonstrations that were not very friendly and all did the same thing. So I bought one, and what I did was kind of created a scenario, and then my friend Rick, the movie guy, he needed some help with it. So we developed some code, and then John wanted to do a full product with it. So one of John's products called Ultimate has a next gen, and you know, how many screens do you have in there? You have a lot. It's 25 or 26, maybe more screens.
Yeah, about that.
It's a lot, but your customers love it, right? And our customers like this because everybody understands touchscreen technology. So one of the things that is important, and John and I went through this, and Josh and I have gone through this a lot, and you know, even recently where we had a change. So John, what's my favorite utility?
Inkscape.
Josh beat you to it. Yeah. So here's the my Inkscape page. So this is how I plan out the screens for the tower. And you know, in what I did, I set up the page to be, we're using a 320 by 240 screen. So our page size is 320 by 320 by 240, and then we just set everything up. And so a lot of these screens, and so Chip, you'll see what the things I was asking about, came from here. So for example, on this menu screen, inside the next gen, they have a button widget that, in fact, I don't even use the button widget. I use the crop widget, which is what we now have in P2 debug. And so that these are off and these are on. So the crop element, it has an unpressed and a pressed image state. And so, you go through and do it all this way. We noticed when we were at that trade show, these corner hotspots were a little tight because, there's a beveled edge on the thing, and, those of us with big fingers are having trouble. So, the nice thing is Inkscape is free. It's super easy to learn and use. And, I do, you can see I mark stuff up all the time. So all of our planning was done in this. What I did, now Josh and I will go back and forth on Inkscape pages, and John and I have done that many times too. For our sales and bosses, what I will do is I will just output these as individual images into a document, and then I'll have text in there explaining what they're seeing, etc. But, you can see, widgets. And I've tried to duplicate this stuff in the P2 demos, but, this is a switch, toggle kind of thing. Again, lots of buttons. Here are radio buttons. On the flag setup, we have flag team colors, so we got a little creative there. And then in the next gen, you don't have to do this. I'm actually using a bit of memory. And here's a screen, for example, that takes, I have 3 images to back it up because we might have disabled devices. And so on the radio check screen, anything that you can't talk to will be in this dark gray, but when you press it and it's doing a test, it'll be green. So there's lots of those things there. So anyway, all of the planning, Josh and I spent a lot of time going over this. The nice thing is you can very quickly put these images into a Next-Gen and do just a little bit of code to link them together so you can see it on the physical display on your desk. There's a bit of a break here because these screens, even though they look very graphical, none of these require an actual full background image. They're just a blank screen. And so, for example, if we're in IR mode, we have, the gun image there. Otherwise, if you're in button mode, you have the button. So again, lots of stuff, but it's fairly straightforward. This is the domination screen. So what happens here is this is where you do long distance shooting. So you shoot at the tower, and so long as nobody comes along and takes it back, the LEDs on the tower will animate upward. And once they're filled, they'll flash. And what happens internally is a timer starts running. So when you capture the tower, it sends a scoring message. I was talking about that earlier. It sends a scoring message to everybody. So your team gets a kill report for it. And then every minute of time after, you get another. So this is a time-based thing. So for every capture and for every minute that you hold it, but let's say Alpha has the tower, so it's red, and Bravo comes along and shoots it. And so what will happen is the tower will be fully lit red, and then you'll see the Bravo LEDs coming from the bottom. So blue LEDs will start marching up from the bottom. Now, if nobody else comes along and Bravo fills it, then it captures. But let's say that the LEDs were only halfway up the tower, and an Alpha, who originally had the capture, shoots the tower, then the red will start descending and refill the tower. So there's lots of fun little animation stuff there, and this is what the screen will look like. Not terribly important because not a lot of people are looking at the screen until the very end. Most of the screen interface are all of these are all the programming things. So in the overall scheme of the program, there's kind of 2 major states. There's editing, which means we're on one of these screens, and we don't really care about that inside the program because this is going through and setting up everything. When the person says ready over here, that's going to go to this screen. And this is an animation. This will be a spinning animation. It will tell you which game is being played. what the ID of this particular tower is. And then these, as I was saying earlier, will indicate the mode. When we go to this screen and the propeller detects that, it will query the memory of the next gen. And if it has changed since it was last saved by the tower, it will be saved to the flash. So we do an auto save. So that you can do your configuration and you don't have to think about a save. We did add a manual save button, but you know, technically it'll auto save. So the games we have are domination, which is what I was just telling you about with that time-based. There is a version of that called Hardpoint, which is domination, but after a random amount of time, and you have to have multiple towers to do this, it will switch to another tower. So the tower will shut off and another one will light up and be active. And in domination mode, we light the LEDs very light white or grayish color to say, hey, this tower has never been captured. Once it has been captured, it will be some team color, but initially it will be gray. And so that's how you can tell on the beginning of a domination game, or if you have a tower to tower move. And again, this is where the XP communications and everything comes into play. We have custom XP messages where the in the hardpoint configuration, there is a master tower and then there are satellite towers. And so the master tower controls the moving around, so that we don't, you know, it just simplifies the code a little bit.
Josh is showing the tower on his screen.
Pardon?
Josh
Oh,
is
yeah.
showing
Oh,
the
nice.
tower.
Here, let me, can I pull up Josh's screen? Yeah. Oh, so Josh, so if you guys can see that image of Josh, what's happening is Alpha has the tower, but Bravo just shot it. So you can see Bravo is coming up from the bottom. So the last shooter color will come up from the bottom. So what he just did is he reshot it with the Alpha tagger, and now it's descending back down to do a recapture.
Cool.
So the boss like this, you know, this is one of those things where, you know, again, some of these features come from online video games that I don't play. And so, you know, the boss will talk through them and then so see now that it's all red. So right now Alpha is in capture mode and the Alpha timer is running. So every minute a kill report will be sent that Alpha gets another credit. Yeah, so, you know, again, in the grand scheme of hard coding, it's not. It's just a mountain of it, and keeping it all organized and clean. John and Josh know me very well. For every 5 minutes of coding, I seem to spend an hour of testing because I just want to make sure it works when it gets out in the field. But, you know, again, this is free and open source software, so I make no money doing this advertisement, but Inkscape is an amazing tool. So in fact, remember I was showing you this. Let me go. I really don't, I can't get to the.
I sent Chip a next gen so he could get excited about it.
Oh,
too.
good. Yeah, it's really fun. Well, you know, and by the way, for those that aren't keeping up with spin tools, Marco has the crop feature native in spin tools. So now he has basic debugging and he has most of the graphic debugging and including the crop stuff, because I tested the crop demos that I did. So Marco's been doing a really nice job on spin tools. So this bracket right here, now, you know, Josh is really good at 3D modeling. I'm not. So you see this face? I created that as a flat vector in Inkscape and then brought it into FreeCAD and extruded it, and then it was done. So I made this in kind of technically 3 steps, because I think if I can move this around, I added, Josh sent me the link to the brass inserts that we like to use. And so I added those in. You know, and the pilot hole for those I cut away so that Josh, because I had sent this idea to Josh and said, what do you think? And about 10 minutes later, he sent me a picture that he had already printed one. He said, yep, that works. So
Nice.
it was it was a really nice quick turnaround. I was, in fact, I called him right away. I was so surprised because Josh is a busy guy, but he was able to put that onto his bamboo printer, and those work really nicely and print very quickly. And we had a model, and he was able to verify it on a board that everything fit. I had just measured, I'd used a caliper to measure from the top of the edge to the PCB plane. That's how I determined this internal height, and it worked.
I think that should be a parallax item.
That might be an idea.
That works way better than my 3M double stick tape that I currently use to hold the P2 edge in.
Yeah, there's already a pattern for this. So it'd just be add the holes, onto that
You put
pattern.
it on the charger in
I put
there?
them right onto the board. They're not included in the pattern, but anyway, it all worked out. But anyway, I think I've worn out my welcome, so I'll stop talking, Ken, unless anybody has any other questions.
Well, good job, John and Josh.
Yeah, John, thanks. That's very neat. And thanks for coming, Joshua.
Pleasure.
Yeah, I read about different types of programmers, John, complexifiers and simplifiers. You're the latter.
Wow, it's because I'm a moron and I can't make
Yeah.
things too complicated for myself.
Good to be
I'm
a
the
moron.
same way.
This is one too. There's a lot of success in this product, you guys.
Yes.
It is a culmination of a lot of stuff over the years. Again, my first DMX code was on the SX, so it's going way back. And everything we've done, and it has taken longer than I wanted, and certainly Josh was wanted, but there's just two of us doing all of this work, and it's a lot. And so, but what we're confident in is that once Josh and I say, okay, we're happy now, we have a whole bunch of tools that will make other development go more quickly and cleanly, and we'll know that the stuff is reliable.
I can appreciate the statement about not obsoleting all the hardware out there by making improvements.
Yeah.
But in keeping with the idea of needing a mini castellated P2 module, I sent you a couple questions by email.
Oh, okay. Yeah, I think that would be, in fact, there was a couple of people in the forums. Now they said they'd pay, one guy today said he'd pay 4 times what he pays for an edge for that. I won't, but if I could get one of those castellated things, the same price as an edge, that would save me a lot of PCB room.
Yeah, that fair design is called the P2 stamp, and I have one laying around here. Don't ask how I get these things, and that's a really solid one. Like, the design is really solid.
Yeah, and it's more compact. I like the edge, but it's in this particular product we have a lot of space. In our tagger we don't. If we want to put it into the existing shell, which is a challenge that the boss has given to Josh and me, and it's not, we certainly can't use a vertical socket in that, and the horizontal socket extends the size of the edge, so we're not sure we can fit that in there either.
So what would this be? I missed what this is.
There is somebody, well, Ada knows him, somebody in Europe, right, Ada, that made a PCB that's essentially an edge, but instead of having, pins on it, like, an old, basic stamp or something, it has castellated edges so that you can put it into a socket. Remember the other day, John, when you asked me if you could take a P1 and fold the legs over and put it in a socket?
Yeah.
But that particular thing that I'm talking about and Ada just mentioned, that
I'm
device fits into a socket.
The storage thing, so I can show
I
it a bit.
like it.
But no, it's gotten entangled with the breadboard. Oh no.
Well, somebody could alert me to that forum link. That would be helpful.
It's supposed to be okay. There we go. Just take the entire thing out. We'll figure it out later.
I like that idea, though.
Well, see, if we take this and we can leverage this, what we'd have to do is, these are on 50 thousandths pitch, but there's two sides of them,
Yeah,
right? So we'd have to have, the castellated edges would have to be like 25 mils pitch. It'd be very tight. It'd be twice the density of this.
No, aren't you, what if?
There
what
we
if-
go. That is.
I don't think they're thinking on pins on just one side.
Yeah, no.
I
You
can't
know,
quite
yeah, see,
find it.
yeah, share it. Please share your screen, Ada, so everybody can see that in a larger view.
Like, it's not a screen share, it's the webcam.
Oh, all right.
I have
I
to
can see
figure
it.
out, is there a way to, there's a way to pin,
So you're in
Yeah, if you
a video
pin
for other
Ada's
people.
screen, you can see that.
what is the pin count on that, Ada?
or I can go, yes, the pin counter, I think that's just an 84 regular PLC
Yeah,
thing.
it's a standard PLC socket, isn't it?
Yes, that's the key. It's a standard socket.
That socket might be more expensive than the module.
Correct.
Not funny.
Yeah, you know, these sockets are
Oh,
cheap.
that's what we want.
They're just
There we
big.
go.
For some reason, it's just really dark now.
Yep, we lost light.
No, it's plenty bright in the room. It's just the camera acting up. Will it implode if I open up it, or can I just go into like the setting here?
Is that about 3 centimeters on a side?
That's about, yeah. It's a normal PLCC thing. Wait, we can get the ruler.
PLCC socket, 84 pin socket as a standard dimension.
There we go. That's a ruler. If you can see that.
yeah.
Look at that, an American who knows metric. 3 centimeters.
Love
Yep.
it.
That's about it.
And that's just it connected to a bunch of. No, that's a P2 eval. That's just I've got one of those video boards connected to it somehow, and one of those
Where's the
USB boards, and whatever the fuck this is. Oh, it's a SD card reader. Yeah, it's an SD card reader.
Look
Why-
like those sockets.
I
are-
think there was some bug with the SD card reader on the thing. I don't remember now.
Huh.
Well, thank you, Ada.
Anyways,
you,
this is
John and
very
Josh.
solid board. It runs very hot, but it somehow still works. Quality.
we have a thread for that, don't we? The P2 stamp.
Yes, there's one somewhere.
I'm hunting.
Francis,
It is just in this
part of it.
very
I
oddly
posted a
shaped
link to
breakout
an
board.
image
Oh, you
of it.
did already? Okay. Hold it.
Like, why is it round?
Okay, well, Chip, do you want to move on to math?
Sure.
Floating point fun?
Yeah, so I've added a few things of late. I just posted, let me share my screen here. Oh, wait a minute. I've made some libraries for doing 64, 96, and 128-bit unsigned integer math, because I've been working on some motion control stuff, and I need like accurate accumulations. Floating point potentially won't do it. Let's see here. How do I share the screen? Here we go. Advanced. Okay. All right, so here's the OBEX. And I just added this thing here, this unsigned integer math. And it has these functions in it that you can see down here. So it has, you know, negate, add, subtract, compare. It has a magnitude thing that'll return the MSB position. You can shift left, shift right. And then there's multiply, divide, which I'll show you the code for that. It's neat how it turned out. And then I leveraged the Cortex solver, which has the log and the qlog and qexponent instructions to be able to, you know, look at the first 27 bits of what would be the mantissa of these numbers, and then do a conversion both ways from log 2 back to exponent 2. So if you want to take like a cube root, you can take a log q and then divide that by 3 using this, and then run it back through here. And it's funny that for taking, because I have some need for square and cube root. Cube root's a lot harder than a square root. But the thing I realized about a cube root is that, let's say you have you want to take the third root. Well, only the top 1/3 of your bits are going to have an MSB effect, except for maybe some rollover conditions. They're not going to have even an MSB effect on the cube root. And it's like in a square root, the top half of your bits will affect the root value. But in the case of a third root, it's only the top third bits. So even though we're only looking at 27 bits of the mantissa, it actually is good for a 27-bit root. So if you cube a 27-bit number, you're going to get, what would that be, 60, 78 bits or something. Anyway, so then we have some little helper things here just for being able to interface, because usually when I'm doing this higher order math anyway, at some point I want to extract something that's meaningful, like a long. So I can grab it by the LSB or the MSB and then get it back into a regular long variable. And then to introduce a number into this into these structures that are 64, 96, or 128 bits, there's this little thing here which you give a long value in a shift, and it shifts it up and then makes the number. Because for a lot of stuff I'm doing, my significant bits in and out are way above the LSB, but I need lots of LSBs to maintain accuracy during the process. So I have this, I want to show you one of these things. Is it, okay, here's some code for like the 64-bit. So this needs V50, right? And why does it need V50? I don't remember. I know I'm using structure, so you got to have something more recent. But you can, in this case, for the 64-bit library, you declare an int64 structure, which has 2 numbers in it, right? And here's a routine that negates. It does a 64-bit not and then a 64-bit increment, which is a negate. Add has to add low long and high long. Sub, same thing. Compare, same thing. The way the compare works is you give it 2 terms and it returns to you -1 if the first one was less than the second one, or 0 if they're equal, or 1 if the first one was greater than the second one. But this stuff resolves to a few instructions. Now it was really fun. So here's the one that does the encoding right here. Whoops. You can see it. I found I can do this like for any number of bits. You can just walk these encode and add instructions along, and encode any size number. Because if it's C, you just keep adding and then you quit doing new encodes on lower long. So it'll do an encode on any size number. And then have a shift left. That was first thing we say, do we have any like whole longs that we're shifting? And then intra-long shifts, where we're moving bits within longs. And shift right Q, same thing. Now here's what was really fun, I thought. So here's a 64 by 64 multiply, right? Because our Cordic only does a 32 by 32. But remember that when you put a instruction into the Cordic, 8 clocks later you can put another one in. 8 clocks later you can put another one in. So this thing winds up taking maybe only 50% longer than a normal 32 by 32 multiply. So these lower ones give out a deterministic long that you simply write right into the lower long of the product. And then the next one can be written, and then the subsequent ones you add in. So this is a 64 by 64 multiply. I could make it a 64 by 128, but my point was not to have, I wanted it like a nice even system where the ins and outs are all the same. Because if I want purpose of the extra bits is I work oftentimes way above what would be the LSB of the number system, so that I'm taking things like remainders in fractional form, which are more usable, because they're already scaled to the numerator. Anyway, so then we have an int. The int, I tried to use our existing divide queue from the Cordic to shorten the process of dividing, but it turns out that you can't. There's not much you can really do. So you wind up having to do longhand division. I did ask, I think it was Roke and ChatGPT, I explained my circumstance. I have a 64/32 divide, but you can't have more than a 64 or 32-bit quotient. And could I leverage this in some way to build a faster divider? And it said, oh, absolutely, we can do this. So it used that, and then it had this little loop there. Said, oh, now we have to run this adjustment loop afterwards. So I asked, well, how many times might that adjustment loop have to operate? And it said, oh, up to 2 to the 32 minus 1, which completely defeated the purpose of making a faster multiply. So, by the way, are you guys still there? I don't see any. Okay, no, I see some movement. So the division has to be done kind of longhand, where you compare, two 64-bit values and then conditionally subtract them, and then you take what was that bit and you rotate it out. And I'm getting negative carry out, so I knot my quotient before and after, so it winds up true in the end, because carry equals 0 when the subtract was able to happen. And then the log stuff here, this just uses regular qlog instruction, and same with this thing here. No need to go to assembly language for anything about this. And then here are little routines that extract and insert your long data into these longer words. Now let me load in here the 128 one, just so you can see the biggest one. Okay, so here's 128 bits, right? We have 4 longs making up 128-bit and int 128. So in this neg one, you put in a structure of 4 longs and you get out 1. So it has to do, of course, 4 knots, and then, or 64 or 128-bit knot and 128-bit increment. The add, no biggie. It's just pretty simple.
Wait, I think the negate can be faster.
Good.
That seems.
How?
I'm pretty sure that I figured out how to negate a 64-bit one faster, and that's that one. I have to check if I've written that one down. But you must think that the neg is really just a subtract from 0, right?
Right.
So it is possible to ripple up that carry somehow.
Well, yeah, it's a knot and an inc. So if the result is 0, that means you have a carry, right? Well, no, would that mean? Yeah,
oh,
that would mean.
I have the absolute here, but it was a thing about the negatives. Wait, so if the neg instruction comes out with a z, that means that
you have to.
It's 0 minus something. If it's not 0, that means that you've got a borrow to ripple up.
Let's see. That would mean that you would just not and not negate.
I have to think about this. Right, I'm gonna write it.
Okay. Well, hey, yeah. Think about it. Do you remember though? Was it a trick that just worked for 64-bit, or would it be extensible so that you could do any number of these?
I think it's extensible, but you need to be a little bit clever, because I think it's like this is for the yeah, it has to be something like this. If it's not 0, then it has to ripple the borrow. So that's it for 64 bits. You see it in the chat?
Yeah. Oh, let me look. Let's see. Oh, gee, where is the chat? I think I don't see. I'm not. Oh, here it is. Here, hold on. Let's see.
Oh, wait, do you need to? I don't know. That
Okay,
is
my chat
correct.
is open.
That should be that.
Yeah, so that's gonna work for
But
six. Oh, you subtract reverse. Can you use it? Can you use an NZ after that? And
wait, no, that has to be sub reverse, I think, right?
you
Or
have
does it?
you have another case after that.
I have to remember this, but there is a quicker way to do it, definitely.
Okay.
I
Well,
do
yeah,
know
what
what the quick absolute looks like. The quick absolute, I've tested that one. That looks like this. Because that's on the website.
Okay, so you do an absolute high, and then if C, you neg the low portion. If C and not Z, then you subtract 1 from the high portion.
Exactly. So that is, but that already negated the high one. So I think you'd need to use a sub reverse for that one.
Yeah. Yeah, I'll have, yeah, you know,
I'll
okay.
have to figure it out.
Yeah, these things are tricky, but once you get it, it's done. Okay, well, good to know. Okay, on this 128-bit, look at the 128-bit in magnitude encode, right? So I can just walk from the high long down to the low one, and once I get a non-zero, meaning the input was non-zero, I just keep adding 32 and I don't do any more encode. So it'll just encode the magnitude of any number of bits this way.
And the encode instruction is really good.
What's that?
The encode instruction is really good.
Oh, it helps out with here. And why did I put the neg M1 at the bottom? Why did I do that? Oh, because I'm getting the, why did I do that? Why did I put the neg?
That's to get the negative
not-
1 if it's 0.
Yeah. That was a 0. Yeah. That's what this was up here. Okay, I didn't understand. Didn't remember. Okay, so shift left, do we shift double longs, single longs, or intra longs? I wish I had made, when I was doing the silicon, I could have made a shift instruction that used set Q in front of it. So rather than brings a bunch of 0 bits in, I could have brought in the Q register, and it would have made like, double long shifts much easier because I could have already incorporated like the next long. But now I have.
Yeah, that's another one to add. That's I think x86 has one like that. It's really useful.
Yep. It's called
I don't
shift
know why we
left
don't have
E.
it.
Yeah.
I
Okay,
guess
so
you can add it without taking an extra instruction slot by sort of repurposing setq plus maybe RCL. That's least likely to come up, probably.
yeah. Okay, you see, this is the 128 by 128. So this could, produce possibly a 256-bit product, but I don't care because, like I said, I want this thing to be unitized to whatever number of bits it is, and I'll work within that. So anyway, I launch here 1, 2, 3, 4, 5, 6, 7, 8, and then I have to start gathering results back before I can launch more. So I do 9, 10. This is the last QMOL right here, and then I gather all the stuff in, add it up. So because I'm only tracking the lower 128 bits of the product, but see it's maybe about 2.5 times as long as a normal 32 by 32 would take. And then check out the 96. It's really simple. The 96 wasn't that complicated. Its multiply was just this. It was just, what is that, 6 QMOLs. And so this probably winds up taking like twice as long as a normal multiply, but 96, in and out. And then for each of for any of the divides, we have to, do them longhand. Okay, so that's the that's the integer math stuff. So let me shrink this. So it's up here on the OBEX now. These are all the functions. And then, and then, these are the files. So I've tested these things out as I was using them. They all seem to work fine. I don't think there's any bug possible, but anything is possible. Okay, so that's these integer math things. So any questions on that, comments?
Can you hear me?
Yes.
Hey, Chip, I just had this is probably dumb, but I was just thinking like the 64-bit system counter, global counter, it's called different things, different places.
Yeah.
That rolls over after a long time, but not infinite. So I just wonder, could you use that with the 128 maybe and make it sort of
Yeah.
basically forever?
Yeah. I mean, yeah, you could, yeah, you mean you want to do math on a 64-bit counter. That 64-bit counter, if the chip's running at like, I think it was 250 megahertz I calculated, it's like 3,000 years before that 64th bit turns over.
Oh, is it
Yeah,
already? Okay, never mind then. It's already.
Yeah, if you're trying to run this something without ever restarting it for like more than 10 years, you should probably use something that's like radiation hardened.
Oh, because it'll probably get an upset at some point.
Yeah, exactly.
Yeah. But yeah, but yeah, Ray, I didn't think of that. But now you could take that 64-bit counter and you can do all kinds of math on it to know, gosh, yeah, just how long will it stay running before a power interruption? That's the bigger thing.
I was just trying to figure out. I was just trying to contemplate I forgot how long the 64-bit counter go. But if it's like thousands of years, okay, it doesn't matter. Never mind.
Yeah, we're never gonna
I
get
mean, you
there.
can calculate it very easily. It's just like 2 to the power of 64
Divided by 300 megahertz.
Yeah, let's go 324. So we have a number of seconds that's very large, so it's divided by 60 times 60 to get hours.
Lots of seconds, and then there's 3,600
24 hours,
an hour divided by
365 in a year.
24.
Yeah, okay, 320 megahertz should roll over in about 1,800 years.
Yeah, that's what I got.
Okay, so that's not a problem. The other question was, you said this was for motion control, and I'm kind of dabbling in pick and place stuff. And I was wondering, like, how would this fit into motion control?
So, so I'm doing motion control from a jerk. I'm driving everything from the jerk term. So jerk integrates into acceleration, which integrates into velocity, into position. So the jerk, by controlling from jerk or beyond, you're kind of minimizing mechanical stresses and cutting out like anything that could be perceived as nearly a step function on the load side. So it's very gentle acceleration, deceleration. But what I have though are discrete time units that are somewhat large, like 1 millisecond. So I need to compute. In fact, here, let me show you. I'm going to move the thing over to where you can see something else here. Let's see. Okay. How do I go? Okay, let me go from here to here. All right. So, okay, you can see this. You see this here, right? These are the equations for, jerk control. So I give a constant jerk input, and then I have the time period. And so with each step, the acceleration advances by j times t. The velocity is advancing by a times t plus jt squared over 2. And then when you get down to this last one, you've got a third degree term divided by 6. But here's the deal. Sometimes I have to calculate this from this whole equation, right? And so it turns out being this deal where you got to take a cube root, and because you're trying to figure out, okay, how many time units. The trouble is the time unit is never going to get you to the integrally correct position that you wanted to be at, because this stuff's accumulating at at, maybe 300 megahertz. And you're changing the schema every 1 millisecond. So there's lots going on that's high speed. And so but you can't change it that often. So you're going to change it every millisecond. So you got to figure out how many time units is it going to take me to reach approximately, so it's like a round function on a float thing. How many time units is it going to take me to get approximately to where I need to be? But I can't hit it exactly. But I have to have my math tracking it at high precision anyway, because I need to know, like, how far did I really move the motor in the end? Because the motor might be moving for 30 seconds or something, and it might have thousands of counts per revolution. So I wanted the really high bit math to be able to accurately emulate what was going on in my low-level motor driver, which is using a smart pin in NCO mode. So every clock, it's adding a 32-bit value into an accumulator and then outputting the MSB. So I have to be able to, so there's some kind of calculus involved, but I'm dealing with integers at the end of the day. So I just needed to know what was actually happening. And that's why I wanted all those bits.
So Chip, is this, I'm trying to wrap my head around this. Is this stepper motor control or direct motor control? I'm not sure what's going on.
So it's not, it's an open loop servo system. So we're giving these servos commands. We give it a step command with a direction state.
Okay,
right?
Regular stepper motor. Okay.
Yeah, step and direction. But we're planning the motion so that we're minimizing, forces along the way. And so this third degree, jerk acceleration to velocity to position thing is a good place to work from.
Is that does that buy you missing steps, perhaps, or?
Well, no. See, you can't get the exact number of steps you want actually, because of the fact that time is so large grained, like 1 millisecond. But what I do is I figure out, I need to know exactly where it's going to go, and then compare that to where I actually wanted it to go. And then I'm going to put out an extra term, which has nothing to do with this math, but that's like a 32-bit tweak term, which will always modulate the velocity. Every time the velocity is changed, I tweak it by a 32-bit value to knock it up or down a little bit so that the math comes out where I need it to be. Because I can't get in raw terms exactly what I want.
And Chip, correct me if I'm wrong, but I think you covered this in some detail in the last forum.
Yeah, last meeting we talked about, I showed some stuff that was about this. Sorry if it's redundant for some people, but anyway.
No, I'm just pointing out in case somebody wants to go back and look at more detail.
Oh, yeah. But calculating this T term is like, you can see how that gets complicated, but you can only work in integral numbers of T. You can't do like 1.1. You're going to do 1 or 2. So that's, anyway, does that make sense? Hey, Ray.
I'm here. It doesn't make sense to me, but I can appreciate it anyway.
Here's what kind of, I kind of knew somewhat of this, but I got clarified just asking like one of the AI, I think I was using ChatGPT. I asked it to explain, how control works, and it knows this stuff. So it can explain it to you exactly at the level you ask, and then it'll educate you, and then in a couple of minutes you'll go, oh, okay, I see how this kind of works. And then,
well, I guess could you just say, is this applicable to like CNC or pick and place?
Oh, absolutely, yeah. What all this math does is it accommodates the reality of inertia, to a nice degree, because you can't, within a computer you can say X is 0 and boom, X is 100, but in the real world, if you want to go from 0 to 100, you have to start from a stop, slowly accelerate, hit your acceleration limit, then your velocity limit, then do something mirrored, maybe going back down to 0 so that you wind up so that your acceleration and velocity are 0 and you've landed at your endpoint.
Okay, yeah. So to me, this sounds a lot like not missing steps, because what I notice is if you try to push the steppers too hard, they
Yes,
lose
yeah.
steps. Yes.
Yeah,
Okay.
that's the point of all this, is to minimize those forces that would cause things to not work.
Okay, I get it now. Okay, thank you.
Yeah, you bet.
Chip, I have a question.
Yeah.
Real quick, isn't these kind of functions, aren't they really relatable also to encrypting and decrypting of data?
Yeah, they could be, maybe.
Because it doesn't take much to shift a binary value or an integer value, shift it left or shift it right to actually do a very simple encryption.
Oh yeah, a lot of those, like SHA-256, it's nothing other than, I think, just like shifts, adds, and XORs.
Yeah, yeah.
It's real simple stuff, but it's really difficult to try to unravel.
Yeah, decrypt it.
It makes a big mess really fast.
Yeah. Well, that was just a very simple, question related off the topic from what you were saying. Did you put exclusive ORs functions in this?
No, I didn't. I just figured it was for like measurement purposes and not really. I could add and or XOR.
Yeah, I think that would broaden your application
Yeah.
capabilities.
Yeah, as it is, it's just kind of intended for tracking values, not.
Right.
Yeah, because I mean, for and or XOR, there's no flow between longs. It's all a bitwise operation, which is really simple.
Right, right. Okay, that's all I had.
Okay, so, oh, go ahead. Someone.
I was just saying, Chip, I just started looking into this open pick and place stuff and, CNC stuff in general. It seems like P2 is like the perfect chip for doing this stuff. And it's kind of like, everybody's set in place already, but I'm trying to, this seems like it's in a way to improve things like for pick and place, the ultimate objective is parts per minute. And if you can, use our existing system and move fast, it seems like this might allow you to accelerate faster.
Yeah.
And increase your parts per minute or parts per hour, I guess is why they do it. But
you can always work up against your physical limitations by doing something like this. You can work right at the limit. If the machine can handle it, you can work at the limit the whole time.
Yeah, I think this looks very interesting to me. Okay, thank you.
Yeah, go to ChatGPT and just talk about jerk and acceleration and velocity. And I mean, I guess there's enough stuff out there that thing's been trained on that it knows immediately the context and the terms and how to explain it. And it's useful. I mean, it seems to me like it makes a custom textbook, a portion of a custom textbook just for you, just at that time for whatever you asked. It's really amazing. I mean, you can learn so much today, and all you got to do is want to know something, and then the means are out there to discover it.
Yeah, I think the stepper motor has like a maximum force it can handle. I guess it's force it can handle. So it just like dies if you try to go too fast. But if you can,
yeah, it'll just stutter. It won't go.
If you can integrate this into that, you can, it seems like you can dramatically increase the speed. So
yeah, as long as if you can work up against the physical limitations all the time, you really couldn't do any better than that. But all that stuff boils down, I mean, it can all boil down to just constant jerk. It's, well, for a given case anyway. And so it's really simple. I think we talked about that last month, and I had some plots that we're printing on debug that showed how all this works, but it's really not complex at all. For me, the hard part is the concepts are easy, but then because we don't have like, a 64-bit NCO in the smart pin, it's only 32-bit. I have to like put other math around it to be able to exploit that smart pin mode, but also track accurately the numerics.
Oh, Chip, what are you showing right now? Is this like, this looks like stepper motor control here. Is this not part of the other thing, right? This
This
is,
here?
yeah.
Oh yeah, it's just some stuff I'm working on for Doug. You know, the guy that does the machine automation business. He used to rent my shop, but he has moved out by the airport, so he's hired me to do some motion control stuff for him.
Okay. So this looks like exactly what I'd be interested in here, right? Okay. Good.
Yeah, it's just really just some concepts, you know. And once you realize the concepts, they become malleable. You can use them and exploit them. Like there's, you know, I don't, if I want to know, like let's say you want to know what's from a stop, what's velocity going to be if everything is 0 and you know, apply this much jerk for so much time. It's simply this. Don't even think about like if you're gonna ramp up and then taper off, that's all you need. That's it right there. So there's a lot of this stuff can cancel out. Then because when you're accelerating versus later tapering or decelerating to a stop, a lot of this stuff cancels out and these equations become greatly simplified. Like, you know, this is something I found here, like just the square root of velocity limit over J is sufficient. I mean, if I wrote out the long term of those equations, it'd look really big, but so much stuff cancels out that oftentimes the stuff you have to compute isn't that complicated. Like this is an algebraic reduction of something that looked kind of, you know, bigger at first.
Yeah, I'm not an expert, but I'm imagining that existing things kind of work at the lower limit of what's possible to make sure that the stepper motors don't skip.
Right.
And if something like this seems like you could take it to the maximum potential.
Yeah, I think where a lot of this work has gone on is like in all these little 3D printers that have been made, you know, and they're probably using like really inexpensive chips that they probably wrote in C or something. And, you know, someone wrote a library a while ago and they've been using that for a while. Maybe they tweak it a little bit, but it takes a little while to get into this and kind of get a handle. I'm still struggling with it. What's hard for me is there are so darn many steps and terms to get something done that my mind always wants to like, what do they say that like one of the big problems in software is premature optimization. I can't help but think about it without trying to think how to optimize it at the same time, because I know there's a lot of redundancy. And so this actually slows me down, because if I were just to do it all longhand like this, it'd be easy to work on. But I'm looking here and seeing that I know there are all these things that can factor out of here. And so this makes it
What I usually do is I make a intentionally shitty prototype, like just the logic in like whatever language is the dirtiest and quickest.
Yes.
It's usually Ruby on the PC. And then when I've kind of got that whole logic working, then I go and then I write the assembly code.
Yeah, yeah. Well, that's for some stuff I do that too. Like I did all that for the Cordic hardware and the chip, because that was, you know, I had to work that way. But
I think the FPGA compiler is like really slow too, right?
Yeah, and getting the concept down was, I used Delphi for that.
But incidentally, I kind of have something that I've been like oddly hyper focused on for some reason for like a week. And that sort of fits into the idea of interesting things that maybe should have been in the silicon.
Oh, yeah, I need to make I need to keep a list of all the things. I'm always thinking of, you know,
I was always thinking of that would be good. So you remember like the funny triangle 3D model rendering, right?
Yes.
So that kind of spends a lot of time just, okay, we've got the UV coordinates, but now we have to get the color from the texture. And that's like a bunch of multiply and adds to get the address. Then it starts it into the FIFO. Then it does something else for a little bit. And then it pops out the byte. Then it looks it up in the LUT. So it gets an 8-bit palette image. And that's the easiest one to do, just because otherwise you'd have to add a shift somewhere. Or
oh, yeah.
to get the correct address, and it'd be annoying. So anyways, so there's something interesting that I've noticed about storing images. You'd have to turn off the screen share real quick if I want to demo that.
Okay, let me
Just
just finish. We'll do that in a second. Let me just
Yeah.
explain one last thing and then we'll go there. Okay, I added in these things. Okay, I haven't released this yet, but you can use these in con blocks and in executable code. So they can, be reduced at compile time to constants if they lend themselves to that. But anyway, there's log and exponent functions for base 2, base 10, and natural. And then there's also a power function, this thing here, where you can take x to the y power. And then that results in these new reserved words. So you'd have to, when I release this, you'll put this thing here in the beginning of your code, and then these are available. This was really challenging but fun to work on, because I use the qlog and the qexp instruction to work on the mantissa of these floating point numbers, and it was so I couldn't figure out how to do it exactly, so I just kind of went by intuition until I started getting it working, and then I honed it in. Then I could rationalize why that was the right solution, but I could not figure out at first how this should work. But they work now. They're all proper. You can take a log of a floating point number, turn it back into an exponent, or run the exponential function on it. And so this is handy. You got base 10 natural and base 2, and then a power function. So if you take like some number to 1/4, you'll get the 4th root of it. If you take it to 4, you'll get the power of 4. Okay, so let me turn off my screen share. Any comment on that? Questions?
You're just keeping me busy in my highlighter.
Oh, yeah, yep.
Thanks, I think.
All right, well, thanks for making the highlighter.
Absolutely.
Okay, all right, so Ada, go ahead.
So let's see if I can, if it works. So there we go. Witness an image.
Hey.
Oh, that looks tasty.
For some reason, like at some point something happened, and now 90% of my photo album is just either plushies or cosplay. I don't know why. Anyways, 24-bit image in 256 by 256. Pretty much perfection, but it takes like 192 kilobytes to store. Or 256 if you're padding it to 32 bits, which you kind of have to in a lot of cases. Not ideal. Okay, we go to...
It's amazing how color can hide resolution deficiency. I mean, that's not really deficient per se, but that's not very high res at all, but that picture looks very
crisp.
It looks crisp, yeah, it looks good.
Look, sorry, I hit the microphone. Yeah, it looks pretty good, right? This is just a high resolution image, just downscaled.
Our brain will make up for it.
Is there a way to center this again? Yeah. Hopefully. So anyways, you can go to 16-bit, which the P2 can also do. You can barely see the difference, probably through the compression. But
this is RGB 16, you're saying 565.
Yeah, this is 565. Yeah, so you can probably cannot even see it when I toggle it. Maybe if I zoom in on like a problem area like this. Everything has problem with red. I don't know why, but yeah, you can see the banding happening. But still, the 16-bit is still fine, and it only takes 128 kilobytes. Okay, but that's still kind of like a quarter of the RAM. That's not good. So we go down to 8 bits, and oh no. So this is 332 RGB.
Yeah, 332. Yeah.
And you can see that it's really nasty. But of course, when we have only got 256 colors, we can just define a palette, right? Well, it's kind of causes problems because then you have this sort of sidecar data that sort of has to be loaded first.
Sidecar data, yes.
But palette is a lot better, but not as good as the 16-bit RGB. So this is at these both are 64 kilobytes, right?
Yeah.
Well, that's still a lot. What if you go down to 4 bits with the palette? Oh no, that's even worse.
Okay, that's a 4-bit palette.
Yeah, you could probably choose a better one. This is just whatever graphic scale does, but it illustrates the point. Now, watch this. This is also 4 bits.
That's 12 bits, so 444.
No, that's just 4 bits per pixel. The same as the
What?
16 color one.
How?
Yeah.
See, there's some
Scratching my head.
funky blocking going on.
But
Oh,
But-
okay. So you have limited domains where like a palette will work.
Essentially, this is called ETC1, which stands for Ericsson Texture Compression.
ooh.
And so the way this works, you can kind of visualize it if you see it very closely. So you split the picture into these 4x4 blocks. And each of these gets 64 bits. That's
Yeah.
fixed.
So a 4x4 is 16 bits times 4 bits is 64 bits. Yes.
And that basically gives, well, this 4x4 block is further split into two like 8-pixel blocks, either horizontally or vertically. You can kind of see both here. So
Mhm.
that's a horizontal split
Yes,
block,
Okay, good.
and there's a vertical split block. And then each of these halves gets a base color. And then each pixel just has to say, okay, I'm slightly brighter, I'm slightly darker.
Interesting.
Oh, that's cool.
They have like a
that-
little
that's
diagram here.
That looks similar to color cell compression, right? Like a
Yeah, it's essentially color cell compression, but without anything.
I think Ray, you had done something about this like a year ago or so, right?
Yeah, I did the color cell. It was kind of just for fun, but I did the color cell compression where you can get HD images that look, in a lot of cases that look really good, and that fit on the P2 chip. Yeah.
Yeah.
So anyways, this is like what the little diagram that they give in the paper. So as you can see, it's really just, okay, we calculate the base color with this sort of block.
Yeah.
There's also this little tiny LUT that's needed to get the modifier values. And you just get 2 bits for each pixel, so 32 in total.
Wow. So wait, okay, now let me ask. You said so 4x4 bit block is the base, but you said there's some half blocks.
Yeah, so that's basically this little big thing that they label as flip bit tells you if the block is split vertically or horizontally.
Okay, so
That
so
really
some
just
blocks are solid. I mean, some blocks are 4x4, and some blocks are split horizontally, and some blocks are vertically, where they have to have like
no,
separate
the sort of full blocks are all 4x4, but each 4x4 block is split in 2 halves.
Okay.
And that only affects the base colors and these coefficient thingies here. They call it table code word. That's just the actual 2 bits for each pixel. They come from the same place regardless.
Okay, so this is a higher quality color cell compression because I think color cell compression is around 2 bits per pixel. I think this you're saying is 4. So
This is 4, yeah.
So this is higher quality, similar thing.
Essentially, right. And the idea here is that you can, it's called texture compression. It's specifically designed for the case where you want to, okay, I want this pixel. You just calculate which block is it in. Okay, then you go through this logic, you get the pixel out.
That's so neat. So a 6, well, gosh, you could make a really good 640 by 480 image that's taking 4 bits per pixel. There's 640 by 240. That would only be 150K.
Yeah, that would just barely fit.
The trouble is it has to be done post-mortem. You have to like take an image and run the conversion. You can't really like draw
Yeah, you need to
from this.
figure this out sort of ahead of time. You can sort of, like each individual block is of course independent, so you can sort of figure out the block that you want to modify, but it's kind of, you'd get sort of compounding errors from that.
Yeah, what's the maximum image size that can fit on a P2 and for like 4.3 or 16:9 format?
Really depends on what you're trying to do and how many colors you're using. There's a 1-bit mode that you can use, so pretty much infinite. Like
A 1-bit mode in color?
Yeah, just
Oh,
you
so you have
can choose the
16.
two colors that you want.
So you have 16 bits per 4x4 array then.
16 what?
You'd have 16 bits per 4x4 array.
No, it's a 64-bit total.
No, I know, but if you have like a 1-bit equivalent,
If you have a 1-bit version, yeah, that's a 16 bits.
Well, VGA, that kind of resolution would be really nice for, HDMI type stuff, because that's kind of like close to
Yeah.
what P2 can do. So that'd be kind of interesting.
yeah, it's really intriguing, but it's like tough to I don't know, to draw from this. It would be complicated. It would slow things way down. But it's for taking an image and making it take less memory. It's like amazing.
Yeah, I mean, if you just want to access a single pixel, it's pretty simple. If you wanted to have this in like the reading pipeline, that would be a lot more complicated.
Yeah.
So you think with the assembly, could you do this in VGA in real time?
Decode it in just like that in real time, possibly, but the idea was, well, things
You'd
that
have
you
to have
may
it
have
stored
been.
that way.
Yeah, yeah. I mean, like if it, yeah, but I mean, if you could show a VGA resolution image over HDMI, for example, in real time from 150 kilobytes, that'd be kind of nice.
Probably possible to do it. I'd have to prototype it, but you might end up with something else because this is really better for like hardware implementation. But you could probably still, no, you'd have to like shift that part up and like,
Yeah, I'm often torn between trying to do the maximum that can fit on the P2 memory versus just using cheating and using PS RAM and doing perfect image. So it's kind of a
Right.
struggle.
Yeah, I know what you mean. Yeah, I
Yeah,
love stuff that has to do with like doing really amazing things on very, very little memory. I love stuff like that. This is a really neat thing.
yeah, that was what I was thinking. If you had an instruction that just where you just put your XY value in and you get at some point later like a color out, that would have been kind of awesome. Maybe just a thing to keep in mind because I've kind of just gotten.
You're saying
on a
for like
tangent.
extracting the color of an existing pixel.
Yeah, exactly. That's what you'd need for like the funny triangles thing.
That okay, but you mean that has already been compressed in a
Yeah,
format
someone
like this?
already compressed it.
Okay, yeah. So otherwise you got to do a bunch of lookup and translation and maybe some scaling.
Yeah, the compression is kind of complicated if you want to do it like properly. You can do it
Yeah.
fast, but you sort of lose out on certain optimal codings because like how do you determine if you want the vertical or the horizontal split? You kind of have to try both.
Yeah. Well, Ray, I remember you posting some pictures of graphics that were 2-bit per pixel that were pretty amazing.
Yeah, I think it was Phil Pilgrim that actually showed me how that stuff works. He knew all about all that stuff, and I guess I learned a little bit from him. So that was kind of cool stuff.
Yeah.
Well, incidentally, this scheme could probably be stretched out to 2 bits if you're like really desperate. Because there's 2 bits per pixel, right? If you make the block twice as large, you're left with 1 index bit per pixel. So you can just say, okay, I want the light one, I want the dark one.
Yeah, so what it has 2 bits per pixel. That's half of the 64. So you got 32 left. Then it has some bits about where to divide left or right. And then you've got somehow, is it like an 888 RGB?
It's essentially 1 byte for RGB each, but it's split into 2. And it's either 2 individual 4 bits or it's 1 5-bit and a 3-bit difference.
Oh, interesting.
And which one you want is kind of selected by the one down here by this thing.
That's so interesting. You know, your eye does not see the missing data. It makes really good sense.
Yeah, it could,
Your
you can
brain.
kind of see it, like it's let's zoom it out a bit. Like there's a few blocks that cause sort of trouble, like all this is just kind of
Right. It hit a bad
it's-
boundary.
that's just, but like this is with the uncompressed version, and this is like,
Okay. That's not that bad.
and you can compare it to like right, if you think about the 16-bit RGB, that one is 4 times the size, so you can store a half resolution RGB 565 image instead, and that would look like that.
Yeah.
So, tasty little food.
Yeah, I think so. I think
That's-
what you're talking about here, Ada, is like these, like it's basically like the, I guess like 90s or 2000s graphics where you had the yeah, the images that you were pasting on top of the 3D stuff was like 128 by 128 type images, right? So I think that looks like what you're going for here.
Essentially, right, yeah. The idea is that I mean, I don't have the proper texture mapping, I just have the environment mapping working right now. But remember the funny teapot demo from earlier. Let's see, do I have a screenshot of that I can just drag in here without changing everything? That would be useful.
Yeah, I'm kind of the 3D stuff you're doing, Ada, is very interesting. So this is kind of cool. I'm glad to see you still working on that.
Yeah.
That's probably, I haven't
No,
really
this is so
worked much on
complicated.
it.
It's complicated because your eyes are like the biggest, like the most impactful sensory input to your brain. And so it makes sense that graphics would be the most complicated thing. After graphics would be sound, I think. And then tactile, and then heat maybe.
Right, that was our funny teapot, right? So this is with raw triangles, just as colors. And but you can also have it as with a little bit of a texture wrapped around it. And that sort of requires that, okay, we know what the U and the V coordinates are. We have to like multiply them together into an address, put it into the FIFO, get out the thing, do a LUT lookup. And right, the palette needs to be loaded into LUT for that. So if you wanted multiple textures, they all have to share the same palette unless you want to constantly reload the palette.
Right.
Because this is Z-sorting. So if you have two things with different palettes at a different depth, it has to switch between them. At the same depth, I mean. So, of course, there's just one thing in this because, yeah.
Yeah, you were able to get a lot better resolution than I was. I just pulled in some raw C stuff off GitHub, and it could do something like this, but nowhere near the resolution you're getting. So this is
and also probably very slow, right?
Exactly, that's what I mean.
Yeah, I got this to I got it to 64 and 60 FPS, not 64 for the teapot thing. And that's with like a lot of wiggle room. That's kind of continued working on that a little bit. I think that I didn't do a lot of it, but let's see what the current performance metric is because I have forgotten it as well. Let's just have a look for fun. Just turn this off and see if I can. No.
Yeah, I keep saying it.
What do you think? I'm accepting bets. Has the fucking data path driver uninstalled itself again? It has. Amazing. For some reason, the data path driver keeps uninstalling itself. I don't understand. I really don't understand. Or do I
I
have
keep
to like
saying it, but
mod
I think the obvious like first like thing to when you connect the 9 degree of freedom or 3 degree of freedom, like IMU to this, and you can show the 3D model on the P2 can show.
Well, there's a problem with that, at least with the current incarnation, because you get like 3 axes of angular velocity from that, right?
Well, some of them are, well, the basic ones are just like angle. So, but velocity would be like
Well, the problem with angles is that if you have got 3 angles, there's actually no smooth way to properly get all the degrees of freedom, because you get this thing called gimbal lock.
Okay, well that's
where one of the
yeah.
axes just kind of stops doing anything sensible.
Well, yeah, there's different. Okay, so when you get into 9 degrees of freedom, you can have gimbal lock, but I think like, yeah, but just being able to show like the position with a 3 degree of freedom thing would be cool too. But yeah,
there's a way to fix that. If you got the angular velocity, you can integrate that into what's called a quaternion. Which is like this bizarro math concept.
Yeah, yeah, yeah. So I played around with that stuff. There's
you can if you have the quaternion, you can generate a transformation matrix from that just as well.
Yeah, I played around with that stuff, and most people they do that and they send it to the computer, and they visualize it on the PC. But I think it'd be cool to visualize it from the P2 instead of just from the PC. So I think it'd be pretty awesome to do.
Okay, we are arming the capture card, by which I mean running the kernel driver installation script for the data path. My computer may explode at this point. Yes, I agree to the terms of whatever. I hate out of tree drivers. They're so stupid. Like, why do they need? No, you're not that special. You don't need a closed source driver. Just put it into the Linux kernel. Like what's so special about your driver that it needs to be closed source?
Yeah, the sensor fusion stuff. When you get to 9 degrees of freedom.
I'm talking about the HDMI capture card right now.
Okay.
It's because I hate this.
Ray, what were you going to say about the 9 degree of freedom thing?
Yeah, then you get into sensor fusion. They call it sensor fusion when you have to mix the magnetic data with the other, the angular data with the.
Oh, isn't that also called like a Kalman filter or something?
I think a Kalman filter is what missiles use. That's like perhaps more. It's a similar thing. Yes.
We have transmission.
My high-powered rocketry friends are always using Kalman filters in their tracking of the GPS information while they're running. I do the only reason I know is I do the app for the Bluetooth ground receiver for the telemetry boards. And so I had to recreate a lot of that math.
Oh, I'm going to also add sine, cosine, tangent, and then arc sine, arc cosine, arc tangent.
There we go. That's what we were at.
That's beautiful.
Spinning deep out.
And yeah, let's see what the performance numbers are when I have to add the debugger, I think. Or do I just need to add the terminal? I think I just need to enable the terminal. I think that's it. Yeah, so this is getting frame times that are they're sometimes scratching on the 8 milliseconds, like 8.2 or something.
It's like 125 hertz.
No, it's like more like 120, 125 probably. Yeah, I'm thinking in NTSC multiples. But yeah, off that, let's wait until one of those really expensive ones come out. Okay, that one's actually 8535 microseconds. That was an expensive one. And that's like 2638 geometry, 1115 rasterizer, and 16,015 just transferring it up into the PS RAM after it's done.
Yes, this is cool. So this is what, I just see this and my first thought is, you get a 9 degree of freedom sensor, you break out the quaternions, which is interesting stuff, and then you can like have the teapot move when you move this little sensor board. That'd be fun.
What I'm thinking of is that I still need to finish some of the other stuff, because right now this is lacking clipping. So if something just goes off the screen far enough, it just kind of disappears, even if part of it should still be visible.
Well, for what I was talking about, for just like visualizing the sensor orientation, that doesn't matter. That's fine.
Yeah, that's fine. But for the general thing, if you like want to draw the inside of something that isn't extremely tessellated, which that can also be useful. You can draw like a little textured box from the inside, and then you can pretend you're like in a place, right? It's called the cube map.
Yeah. Oh, Chip, I have a question for you. Do you know about this quaternion stuff?
Yeah, well, Andre Lamoth used to talk about that, and he kind of explained it to me, but I've never used it, so I'm not really understanding. I know what it's for, but I don't know how it works.
It's fun stuff, and I guess you remember the Parallax had like some of those first flying bots, and I guess that used that stuff to work. So that's kind of
interesting.
Yeah, so they did it on a P1 in assembly, the quaternion stuff, and it's so that's you think P2 could do it a lot better, but so I tried in just basic C and it kind of works, but
yeah,
you think in assembly you could do something better, but
way better, yeah.
So the other thing after the missing clipping is that this needs, like, I think I need to write something that really integrates this with the PS RAM control. Because right now a lot of the memory is actually spent sort of just buffering all the triangles after they've been sort of created.
So Ada, is this texture related to the stuff you were talking about earlier? Was it 128 by 128?
This is like a 256 by 256 texture that's sort of wrapped based on the normal vectors.
Okay. That gives a little bit of I don't know what, a sheen or something to the surface, I guess is what you're saying.
Yeah, it's literally just a picture. It kind of gets wrapped around.
What is the picture? Oh, go ahead, Ray.
No, there's a lot of interesting stuff they do there. Like there's bump maps and normal maps and all kinds
this is just the cheapest possible environment map. Well, the actual picture is kind of nice. Let's see where do we have that. It's called something. Did my file disappear, or am I just stupid?
So in this image, are you having like light? I think I'm seeing like 3 light sources maybe. Is that what you're doing?
This is just all baked into the image. This has the downside that you can't, also whenever I launch a Wine program, the P2 resets for mysterious reasons. But I want to look at this image if you haven't seen it. So does it work? Can it capture graphic scale? No graphic scale capture. Why? To paste it into GIMP.
Yeah, I love this image stuff because I was like big into ray tracing and stuff like that. But these days, it's like these graphics cards can just like do amazing things.
Yeah, the graphics, they can do amazing things, but they don't actually use them to do amazing things. They just use them to make shit that runs poorly. Kind of interesting.
Yeah, I wonder like how how many orders of magnitude what we perceive as our computer performance is compared to what it could be if things were truly optimized, like, you know, from the bottom level on up, but using the same silicon. I wonder how much.
Yeah, probably quite a lot. So there's like, well, it really depends. If you're thinking about graphics, there's always the thing you can do like an expensive like ray tracing thing to figure something out. You can also just like paint something on the wall.
Yeah.
That looks basically the same.
Yeah, that rendering stuff has been pretty optimized, I think.
Well, it's kind of going into this direction where they just do all this stuff that's kind of dubiously useful and very expensive, and then the entire thing looks bad because they have to like render it at a really low resolution. Then they use some sort of smooch filter to scale it up. And now they have the next amazing invention that they have is like AI frames. We're like, okay, so we're running it at like 30 frames per second, but what if we make it 60 frames per second? We run an AI thing on the GPU and it like figures out what the in-between frame should have been.
Oh, I get it. So they can keep rendering
like
30.
How? How is that faster than just rendering the frame? And of course, it kind of defeats the point because you have to have fully rendered the second frame before it can start working on the intermediate frame. So instead of showing that second frame at that point, you start working on the intermediate frame. So it's got this latency to it. And of course, that intermediate frame is like gets easily confused by anything.
Well, yeah, and those frame delays, they really impinge on the playability of games, I would think.
Yeah, it's kind of maddening how little care there's put into that.
Yeah, I see things, they look better and better. Like my son would play games on the PC and they look better and better all the time. But I don't know that the playability is getting any better at all. It might even be going backwards.
I mean, it really depends. There's a lot of, that's kind of like a whole topic. Like, is game design going down the drain? At least with like the big commercial games. Because a lot of the times it's kind of just don't even want to talk about that. That's kind of that's nasty. But anyways, that's the image on that teapot. As you can see, it has.
I'll just chime in. I think games are getting better and better all the time. Because I mean, when I was a kid, I played like a football game. It was like a 4x9 LED array on the thing. So
I remember those. Yeah.
So this is
like a bunch of dashes.
Like Minecraft is like a million times better than that. Yes.
It is, but what I'm thinking about is yeah, the graphics have gotten better, but the trouble is, let's say it takes 3 frames to, you know, get an image out because of all the stuff they're doing in the video. Well, it can't, everything you're seeing on the screen is incorporating your input from maybe 3 screens ago. So that's like 16 milliseconds times 3 is 50. It's a 20th of a second, right? Whereas if you go back to like 1980 and you played a Tempest game, one of that coin-op video game, you know, the XY vector color display, I was really good at that game. I could get up to like, I don't know, wait into the invisible levels and all kinds of stuff.
But have you seen the Tempest 2000 port that I did on the P2?
It's pretty good. Well, back in 1980, my point is that the reaction time, I mean, it was like, you know, in the several milliseconds.
Yeah, that goes really fast.
Boy, yeah, that's a very interesting point, because I think the human response time was like 100 milliseconds, but these days, like, everybody's trying to make stuff that's faster. Like, they're doing 120 hertz update LCD screens, doing fast mice and keyboards, but are you saying it was actually faster back then? That'd be kind of interesting.
Well, because of the response time. Let's say they're doing 120 frames, but it takes them 4 frames to get an image out. So that there's like a time delay, you know? So it's really like not any better. And plus, you think about those old vector graphic games like Tempest, it was drawing the lines on the screen. it wasn't even waiting for a raster or memory or anything. It was drawing them, you know, in a quick loop. So I would say that the reaction time between like what you did on the controls and what you saw on the screen and what was then incorporated into the game function was like maybe 10 milliseconds or something. It was super fast. So you mean if you had like really quick response reflex, it mattered a lot. Whereas these games today, they show all these first person shooters are super complicated with these big things. And I think there's like much more time delay from when you move something on your controller to when the character you're on this that is you on the screen actually gets to do anything.
Yeah, there's quite it tends to be a lot, even for like really simple games. Just the fact that it's running on this PC with its like funny multitasking operating system kind of causes problems. So on the first level, you have like the controller, right? Most control mouse and keyboard. Most of them poll at like 125 hertz. Remember, USB.
Yeah.
It's possible to set it in the descriptor to be 1000 hertz, and that's what all those gamery kind of mice do. Interestingly, very few gamepads do that for some reason.
But there's a giant group delay on the data, so it doesn't really matter.
Well, anyways, whatever data you're getting in your the PC's processor is getting, let's just say that, can be up to 8 milliseconds out of date. And because this isn't synced to anything, sometimes it will be not out of, it will be instant, sometimes it will be 8 milliseconds out of date, sometimes it will be 4 milliseconds, it doesn't respond consistently. Then like the data goes into some sort of kernel driver and comes out of some sort of SDL API or something, right? Where you poll it in your frame loop. So there could be another 16 milliseconds on top of the 8 milliseconds worst case. Where the input has just been sitting around. No, that's not 6. That's another 8 milliseconds only, because you can't get data that's that stale. So you can get up to 16 milliseconds flat stale data from your read function. But sometimes you also get like really fresh data, which is almost worse than having a constant delay, is having the delay change.
Well, yeah, because I noticed a long time ago playing around with these multi-arcade machine emulators is that there were these problems that I was like, oh, great, we got this whole game, I can play it again. And it just wasn't fun because I felt like it was like there was a pillow between me and the control, you know, like it just wasn't snappy like I remember it being. And the snappiness is what made the game fun originally. And then when that goes away, then it's just sort of like, it's just not that engaging anymore because you can't work with it.
Well, that's an interesting point, because actually, I think it'd be great if there's a P2 version of MAME, but I mean, honestly though, the old monitor. So I have actually a Donkey Kong machine here, but so it's well, it was originally Donkey Kong anyway, but now it has MAME. But it was I mean, the monitor is like 60 hertz, right? So that's like, I think if I did that right, that's 166 milliseconds.
That's 60 milliseconds for a 60.66 something. It really depends. The monitor isn't really 60 hertz. It's a sort of range, and the video signal is what determines the exact rate.
So I'd be really interested if the old machines were actually more responsive than the new stuff. I'd be interested in that.
Well, and, you
interestingly, if you run something like my funny emulators, they should be within a millisecond roughly of the original hardware that they emulate. And that mostly comes down to the
well, I'm sure that's true.
Driver.
I'm sure that's true, but I mean, like my son playing Fortnite on a high-end PC, is that less responsive? That'd be interesting if that was true.
Probably, very likely. Just because you get these pipeline rendering kind of things.
Well, not only that, when you go out to the TV to display it, the TV might be a couple frames behind too, right?
Yeah, if you've got a shitbox TV, then it will do some sort of smooch filter on the image, and that will take extra frames.
Well, the gaming monitors, they're always talking about how fast they are. So
yeah, those are pretty much all direct scan out. So they don't. You can kind of see I have to say it again. If you run something on like the funny P2 emulator that has like a flickering sprite or something that turns on and off at exactly 30 hertz, well, not exactly 30 hertz, exactly half of whatever the game's frame rate is, and you just plug it into like a monitor, you'd expect it to just, be consistent. But if the monitor or the TV sucks, then you get these little hitches in the flickering because it's duplicating or dropping a frame, which is like, no, bad. Incidentally, if you run anything on a PC, even if the monitor is fine, it will do that just because it's a PC. It will just eventually drop a frame.
Yeah, see these group delays on like monitors, there's little talk about that, but that alone, a monitor that delays 4 frames because it's doing some kind of image enhancement is going to wreck the gameplay. Because that's going to...
A lot of TVs do have like a game mode setting that disables most of the smooching, but there's something even more secret. This is incredibly secret, but somehow it works across all TV brands. So there's like usually a feature where you can assign a sort of type of device to each input port, right? Like, oh, this is where my VCR is connected or whatever. If you go in and select the PC setting for an HDMI port and send the right type of signal, that will actually disable all the smooch filters, or at least most of them. For some reason, this works on like LG TVs, this works on Samsung TVs, this works on other brands as well. Somehow they all have this feature, and they all have this sort of hidden sub feature where if you set the input to a PC, it will disable smooch filters. Why does it do that? It's because PCs often do like the subpixel rendering for the fonts, right? Where it uses little RGB values to tweak sort of the appearance of the pixels, because the RGBs on the screen, they're not perfectly in line, so you can use that to gain extra resolution. This looks like absolute shit if you do any sort of transformation to that. So that's probably why they add that. So just pass it through like a regular monitor would do. And that's usually what you actually want. That's even better than the game mode, where you should turn both on for.
Yeah.
For least possibility of smooching. Like
that image you have on the screen, so that's the texture that you're wrapping around the teapot, but it looks like it's pre-lit.
Yeah, exactly. This has the lighting on it. That's the whole trick why that demo looks so cool.
Okay, so what you're doing is you're rotating that thing all the time across the surface of the teapot.
Basically, each vertex has like a normal vector that's pointing out of the surface, right?
Yeah.
This gets transformed into the viewer space, so that if it's like z equals -1, it's pointing directly at the camera. If it's z equals 1, it's pointing at the back, and then the XY coordinates sort of up and down, left and right. We throw away the z. Fuck the z, we don't need it. Then we take the x and y coordinate of the vector and sort of scale and offset it, so that 0 is 0 xy of the normal vector after transformation is half uv of the texture. And then we just sort of scale it so that maximum normal up is this part, maximum normal down is this, and
Yeah. This is actually like a sphere or something rendered, right?
Yeah, this is just a render of a sphere with some stuff reflected in it.
With some overhead fluorescent lights.
I think I can find where the scene file for that is. Let me see if I can, because that's actually really cheap. I made that myself. I make everything myself, unless it's unless noted otherwise. Because doing it yourself is good. You learn something. What the fuck opened up there? Oh yeah, that's. So let's see. Can I screen share my amazing Blender? Wonderful. So this is the layout. It's a box with some stuff in it.
Oh yeah, there are the lights up on the ceiling.
We can enable viewport shading. Oh no, my PC is exploding. Oh no. Is it? Am I still there? Or has the PC
Yeah, I can
exploded?
hear you. I can hear you.
Okay, so it's just a program having a normal one. Hello?
Yeah.
No, I'm talking to
Oh.
the program. But maybe I have a little bit too much stuff open, including 2 more of this program, which is like takes a million resources. Oh, it's compiling shaders. Now we're going. Oh, we've got the ball, and nothing else. Everything else is Gonski. When did that happen? Hello? Where's the room gone? Did I like end up removing the image that it's supposed to be using? Maybe the image moved to somewhere and now it can't find it. Maybe that's the problem. I don't understand what this is, what fucking problem this is having. Anyways. Maybe just restart it. No, I don't want to save any changes. I don't even know what changes there might be. No, that's the teapot. No, that's the wrong file. Okay, can we have? No, the texture is there, definitely. So what's the problem? What's the problem, John? Hello? Why is this not rendering? I don't understand.
You're not sharing at the moment anyway, right?
Oh yeah, I know why it's not rendering. I actually disabled the rendering, so I get a nice background. You see, I only want the sphere, right? I don't want the stuff that's actually in the background to interfere with the sphere. Ideally, I'd actually turn off anti-aliasing, so I just get the sphere without the gray background sort of bleeding into it, but I don't, there's probably a setting somewhere to do this. But what I need to do here is go to this. Is it under material or do I have it under? No, I probably have it under objects, visibility, ray visibility, camera. There we go. Now we have a box. And that's just the room that's based on this. And then there's like a funny material on the sphere, which is based on some textures that I found somewhere. Probably used incorrectly, but yeah, if you say render preview, then it will actually have the correct thing. It will also look like this. This is really noisy because this is actually ray tracing it.
Oh, it is ray tracing it?
Yeah, this is ray tracing through cycles renderer.
Look at those funny edges on the light sources. I wonder why that's happening.
I have absolutely no idea, and
maybe it's limited precision of the X, Y, and Z step for the trace.
If I go to material, what the heck has happened there? I think there's a problem with the height map of the stuff. Like there's a height map on that stuff, and it's sort of moving the vertices in a slightly weird way. I don't know if that was there before, if I'm just stupid, but I don't know why this has to have a height map anyways. Yeah, and it doesn't matter for rendering the effect, so I guess it's fine.
Right.
So because that just looks like this. And yeah, that's how it renders that.
Can you put some really colorful wrapper around the teapot? Like some texture that's just super.
I think we had that last time. Let's go back to the teapot. Let's see, where do we have it? That's the only one of these proper sphere textures that I've got laying around. I have to find where's the capture window again? Oh, it's turned blue, I remember. I have to launch it again. It's turned blue. Okay, so that's our pot. He's our hero.
Yes.
Let's see, we did have like a grid texture, didn't we? Yeah, we have. Let's change this to say grid because we love grids. This even has text on it, which kind of reveals how
Interesting.
this works. This is just texturing of the normal vectors.
Yeah.
I should add regular texturing. I think the code actually supports it, but my stupid model converter doesn't.
Yeah, it seems like you're stretching things across the bottom at a really high rate.
Yeah, because that's mostly flat, right? Now, there's a better way to do it that I haven't figured out, because if you just look at a flat mirror, right, it doesn't just have one color.
Right.
And that doesn't just have to do with the parallax of the mirror, I think. So, I think it's sort of, there's some sort of perspective thing that I'm not taking into account with this.
Yep.
But that probably makes it more complicated. Because right now, this is very easy to slot into the code. Just take the transformed normal vector that's in camera space and use it to compute the texture coordinate. Because if it was perspective, then it would have to do some perspective math first and then go back to the texture coordinates. But the perspective math is already putting the texture coordinates in perspective. Maybe that makes no sense without scrolling into it.
How did you get the data for the teapot? Was this something available online?
Yeah, that's just the Utah teapot. That was like one of the first 3D models that was ever created, but this is kind of like a nicer version.
Okay.
That someone triangulated. I think the original one used like splines, so you could sort of do curved surfaces without like lots of data, but that never sort of caught on as like a general thing. So this is just a triangle version of it that I found online. Let's see.
Yeah.
So this is the code, and the part that does the interesting thing here is which one? It's in the geometry microcode, and it is do env map. And this is just how I wrote it. It's a move, a scass, an add, a move, a scass, an add. Amazing, right? And it takes this ntx, nty variable, which comes from where is that? From tran nrm. And this is just a normal vector transform using mults instructions.
Okay.
This is just a matrix multiplication. Well, matrix vector multiplication.
Is 16 by 16 bits sufficient, do you think?
For this stuff, it's well, the normal vector is actually only 8 bits, so yeah. But what's kind of annoying that you can't range up the it's a signed 8-bit value. You can't easily convert that into a full range signed 60-bit value. It's kind of annoying. But for general positions, it's fine, because imagine each object, each model has its own 16-bit coordinate space. And usually detail is sort of like, you wouldn't have a huge model with tiny details, and you wouldn't have well, you would have a small model with tiny details, though. So if you just set the scaling correctly, so that that 16-bit cube has the right size around the object, then you can kind of then it's enough precision. For the matrix multiplication, I'm not sure if you chain enough of them, it might go kind of wobbly.
Right.
Speaking of things that are really annoying, that should have probably been in the silicon. We have this multiplics and stuff like that. That's like sequence to do multiple multiplications. Why is there not one that does that for like a 32 by 32 multiplication?
Yeah, that's a good question.
Because I need to do a 32 times 16 somewhere here in the raster code. And I don't just need to do one, I need to do 4. So I do this amazing sequence, while the actual multiplication is just this 6 instruction beauty. And that takes 12 cycles. So if there was something to do that in like 8 cycles, that would already be kind of a win. Because this is in like the critical overhead path.
Right. Can you zoom in on that? Can you zoom in on that piece of code so I could see it?
Oh yeah, we can make it big. Oh, no, that's too big.
Okay, so you're doing, oh, I see. Okay, so you're storing 16-bit values. Oh, I see what you're doing. Okay, so you need to, you need a mol that could extract from a word field.
If there was anything to do to make this faster, because it's kind of really annoying. This could just be like, it could just replace this part with, I could replace this part entirely with a Humal slope bx by span start, get qx rasv. That's sort of ostensibly does the same thing, but this takes like 50 infinite awful crap cycles.
You know, you can load the Portic pipeline up, right?
Yeah, I could, but in this context, let's just undo all of this. That's actually just bad and worse because so span start is only known after we did the span computations, which are outside this for reasons. And we need these RASC, RASV, RASU, RASL values. We need them in these QDIFs. And those are already like pipelined, right? And so if we did any sort of, all this sort of setup here takes less than a single Cordic operation. And that single Cordic operation would be needed if you wanted RASC ready, but also we need RASC and RASV at the same time. So it's kind of like,
yeah.
Because we always need the Z, of course, because which is really 1 over Z, and this V is really V over Z. But that's just how I decide to name the variables. And it if it divides V over Z by 1 over Z, it gets out just V, right?
Yeah.
And it needs to actually do that for every pixel to get the perspective correct interpolation.
Yeah.
Because it's kind of like hyperbolic in how it goes across the screen. So there's this sort of annoying block of multiplication, some of which some of the adds and shifts have been sort of nestled in down here. But there's still this just annoying block of annoying multiplies that have to happen before anything can even start preheating.
Right.
And down in here, there's just a bunch of all the other nonsense, like we can figure out what pointer B should be, because we're waiting on that first QDIF to come back.
I see.
And that first QDIF comes back exactly here, which is immediately after the next one has already been pipelined. And that's the other thing I was talking about. So this, let's see if I can do this. This. No, it can't do it. There's a way to multiple select in this, but let's just go this way. This one, these two, and also these two. That's all what that's just to compute, to start up the FIFO to read the texture.
Yeah.
And that's kind of the optimized version where okay, each pixel is a single, each texel is a single byte. Because otherwise we'd have to add a shift somewhere in there.
But you could pipeline those, right?
This is pipelined. That it does after this.
I mean, oh, it already is. So you're doing a QDiv, and then
this catches the previous QDiv. Right, so on the first iteration, this actually gets the QDiv from way up here.
Okay, I got
Which you need to do the multiply to get to.
I gotcha. Okay, so you already.
It just happens to be exactly like that.
Yep.
This total loop here, this pipe text loop, is 56 pixels. The other nasty thing is this stupid sequence to actually get it back out into memory, where it has to first squeeze, then it has to initialize the FIFO again, because we just trashed it with the texture read, and then it has to conditionally write the pixel into the FIFO. It could use a regular WR word, but that would throw all the timing off. So it does the FIFO thing.
I see.
And then it sort of switches between read, write, read, write, read, write, read, write very quickly. Also, there's this add pointer B that has to sort of be scuffed somewhere in there, because none of this will otherwise increment it. And of course, this is a pre-increment because it's up here. It has to be up here. So somewhere else it needs to subtract 2, otherwise the positions will all be off. And that makes up this sort of final block, which is just the actual computation. Like it is the actual pixel shading. It reads the palette. It does this shading operation, which also does the differing sometimes. It squeezes the result, and then it needs 4 cycles to sort of queue it up for writing. And those 7 cycles, they're kind of annoying, but also they do a lot. In this case, the really annoying part is that you only get 2 operands out of that in a way that isn't entirely useful, because this needs to add the differing before the RGB squeeze, otherwise you get the banding. Bad.
Yeah. I wish I had made the RGB squeeze go to 555 and not 565.
The 565 is fine when you do the differing, because that sort of smooths it out.
Yeah, I just don't like that it toggles between like purples and greens as you go through the grays.
I had a thing somewhere with where I tested the different diver matrices. I fumbled with that just the other minute. Where's that? The problem is that the diver matrix can only be 2 pixels, because otherwise I can't XOR the bottom bit. And also each additional thing would need extra setup time, because so it really needs to be a 2x4 diver matrix, which is kind of odd and unusual. I had this under old diver test. So let's see, that has to switch back to this program. Oh no, today all the stuff gets the time to shine. No, there's my GIMP. Can't forget about my GIMP. Let's see. So this is testing all the this up here. This is just normal gradient. This is no differing. This has this purple, green, purple, green, purple, green, purple, green.
Yeah.
This is just, I think, basic sort of checkerboard differing. Bad, still has the purple, green. And these are all the different patterns that I tried out. And this one here That's the one that I'm actually using.
Okay.
This sort of has a nice sort of cross-hatchy kind of look to it.
Yeah.
There's also a version of that where it does like a radial gradient, and you can see that looks kind of mega scuffed without divering. But also the divers don't do very well on it. So that's the checkerboard thing that's kind of garbage. That's the other thing that's kind of garbage. And that's the one that we end up, I think.
Oh
which
yeah,
is
that
kind
looks
of
good. Yeah,
it does a
that's
decent job at it, yeah. For
Yeah.
being like a weird odd-sized matrix, it also has to deal with the fact that the each channel has a different quantization. I think I had a different variant that sort of inverts the red and the blue channels to each other, which makes it less, which puts the error more into the chrominance rather than the luminance. Which is also a version, I don't know where that is, but it's hard to show that sort of thing over compressed video stream. But you can actually
Yeah.
mess with this at the bottom of this program, because that's the diver matrix. Now, part of the problem here is that this can only add. So think about it. If you can only add, then the color that comes out is always brighter than the one you intended. Or at least if you don't prescale the thing that comes in, it's kind of hard to understand. But basically, you notice that if you put in, there's a limit, right? Where if the number, it's kind of hard to explain this. If you put in something like F8 as a byte, right? And convert and crunch that down to 5 bits, that's already white. There's no amount of dithering that can make it go higher.
Right.
So everything's sort of bright and sort of clipped. You can of course just design around that, so that it's just part of how it's supposed to be. But it's kind of nasty. To counteract that, you'd have to also be able to subtract in the dithering, I think. So that's also another thing that could maybe have been done, like a write with diver instruction. Incidentally, there's also something vaguely related. Where do I have that? Where do I have that? Why does that all show up on the screen capture? Why does my screen capture show things that shouldn't really be shown? That's no good. I hope I don't have anything. No, I don't have anything weird open. Just have a video about a guy complaining about, yeah, that's the thing we had earlier about the graphics that are like too slow. That's what I was watching before. That guy gets really worked up about it. Doing the good work. I am coming for another paper, because papers are where knowledge comes from. Did we already have this one? Yes, we already had this one. I didn't even have to go searching for it. My life is a lie. Wait, it should be in the recent documents anyways. Or it should just already have been. Why do I have just don't. I am beyond asking questions anymore. My life just happens to me. Anyways, paper. The compact YCOCG frame buffer. So this is kind of differing adjacent. The idea these guys were having is like, so YCOCG is kind of like YIQ, but all the coefficients to convert it. All the coefficients to convert it are integers, so it's quick. Not integer, you know what I mean. No funny random numbers.
Yeah.
And so the idea is you take Y on every pixel, but you only store CG on even pixels and only CO on odd pixels. And then you run like a, where do I have to picture, like a wacky filter to figure out the missing values. Now this is a 2D filter. I actually experimented with this. That's what I do with my time, by the way. I read random papers and try to reproduce them. You can actually just use the horizontal column, so you could sort of do it on the fly while reading it. And basically the idea is just, okay, which one of the pixels next to me is more similar in Y? So take the other chroma value from that one. If both are similar, then average it. And that kind of gives a lot of result. And so this takes the same amount of storage as the RGB 565, but it can do smooth gradients without dithering. Which is actually kind of interesting, I think.
Yeah.
And do they have the YCOCG matrix in here for funsies? Oh yeah, that's the YCOCG matrix.
Let's see.
So Y in this case is a quarter red, half green, quarter blue, which is kind of dubious, but so is doing this with sRGB values to begin with. It kind of undervalues the red a bit. Yeah, that's really interesting. This is called this by this guy and also this guy in Athens.
Ada, did you learn about matrices in school, or is this something you just picked up?
I think I just picked it up. I don't know. I just pick things up all the time. It's just like I think it's very useful to know a little bit of everything.
Yeah.
And then sort of go into the interesting bits as they come out. So for some reason, I can tell you a lot about very specific things, but I can also know a lot of like general things.
Yeah, well, I have that kind of knowledge too. Okay, well, hey, we should shut down. I got to do some more work today. I've been promising Doug I'd have his thing working, and I still got some work to do on that. But
oh, what are you trying to get working?
This motion control thing. Just really, I got the control part, but the motion planning is the hard part. So I'm having to, we have like an initial jerk, a terminal jerk, initial acceleration limit.
They also have the T-put.
Terminal acceleration limit, then a velocity limit, and I have to come up with a plan, and then a distance. So I have to come up with a plan to get from A to B in the minimal amount of time. So I think I've got it all down. It's so hard to think about, but I've been like breaking it down, had some epiphanies here and there so I can start attacking the problem. And now I'm down to the point where the last thing I have to do is I have to reduce VLIM if I can't make it. If I can't get to the velocity limit, then I have to control the movement. I have to land on the right distance by controlling the velocity limit. But there's no direct way to do this that I know of. But I was asking ChatGPT, because what this winds up being is a system of equations, right, to come up with something. And there are three different terms that may not even exist. I don't want them to exist under certain circumstances, like portions of the movement, like when you're cruising at velocity, or when you're holding acceleration at a level with zero jerk and you're allowing it to accelerate or decelerate. So there are these time periods that may not be part of the whole final motion plan, but it's like, how do you algebraically manipulate these if-then circumstances? So I asked ChatGPT about this, and said, oh yeah, absolutely, this can be done. Here, for example, like say you have a term that you want it to be 0 if it's negative, otherwise you want it to be itself, right? Can you think of a way to express that algebraically?
That's just like the min function or the max function. I forget which one.
Yeah, that's that. But something that's purely algebraic. So here's what it said.
I'm pretty sure that exists as a.
I think there are min and max, and there are some rules for manipulating those things.
Yeah.
But it came up with a super simple example. Like imagine this. Imagine you want A. You want A to be A. Unless A is negative, then you want it to be. Then you want the output to be 0, right?
You can do it with an absolute somewhere.
Yeah. So A plus absolute A over 2. So if A is whatever it is positive, you get 2A over 2, you get A. But if A goes negative, the numerator cancels itself out because like -5 plus absolute -5 is 5. -5 and 5 are going to be 0. So you get 0 that way. But see, that can be moved around with algebra rules. But I think my problem is even a little more complicated because I have to like iteratively go back. It's more like a convergence kind of problem, but I'm really interested in finding a solution that I can solve in one way deterministically, like step boom, 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 here's the answer. So I need all of my terms. I need like all those terms that I mentioned and the times to go with them. If I can do that, it'd be very, very neat. Then I can just deterministically solve this complicated problem every time in the same amount of time without any iteration. Anyway, okay, well, I gotta go. Thanks for coming, everybody. And thanks for showing us all this stuff, Ada. This is just really interesting.
Yeah, sometimes I just read stuff. And you come across these like really interesting solutions that kind of you don't really think about that much.
Yeah.